Hello there and welcome to Physics with William. Tonight, or perhaps this morning, depending on where you are and what sort of sleep schedule you and your conscience have agreed upon, we are going to spend some time with one of the strangest limits in nature. It is a limit so famous that almost everyone has heard of it, even if only in passing. Light has a speed, and nothing with mass can reach it. That is the simple version. It is tidy, memorable, and a little suspiciously neat, like a sentence that has been repeated so many times that people stop noticing how strange it really is. Because if you pause for a moment and look at it directly, it is not obvious at all. Why should the universe have a speed limit in the first place? Why should there be a final line beyond which motion simply cannot go? Why should light of all things be the thing that sets that limit? And why did some of the deepest answers to those questions end up tangled with the work of Richard Feynman, a man who could explain physics with extraordinary clarity while also giving the impression that the universe was a very serious place that had accidentally hired a very unserious guide? So that is where we are headed. Not in a rushed way, not in the kind of way where someone throws a dozen terms at you and then runs off before you can ask why any of them matter. We are going to move slowly. We are going to stay close to the physical meaning of things. And we are going to treat this less like a lecture and more like a late-night conversation about one of the most important rules reality has ever decided to enforce. Before we go any further, I want to ask you something simple. Where are you listening from right now? Are you in bed, pretending you are only resting your eyes for a minute? Are you in a chair with a blanket, trying to be a responsible adult who merely happens to be horizontal in spirit? Is it raining outside? Is the room warm? Have you already turned over the pillow to the cool side, which remains one of the great triumphs of practical science? And perhaps the more interesting question is this. At what pace does time feel like it is moving where you are? Does the evening feel slow? Did the day disappear too quickly? Are you listening at the end of a long week that seemed to stretch forever, or one that vanished so efficiently it feels like it may have skipped a step? That feeling matters more than it first appears. Physics often begins with things that seem ordinary: motion, time, distance, light. The things that make up the background of everyday life. Then, very gently at first, the ordinary begins to slip. You ask one more question than usual. You stop accepting a familiar sentence just because you have heard it before. And then one evening, quite without warning, you realize that the world is not merely more complicated than you thought. It is more organized, more stubborn, more carefully built around rules that do not bend just because human intuition would prefer them to. If you find this kind of thing soothing, or useful, or simply a pleasant alternative to staring into the dark while your mind attempts to review every awkward conversation you have had since early childhood, do consider liking the video and subscribing to the channel. It helps more than you might think, and it lets me keep making these slow journeys through physics, time, space, matter, and the occasional idea that sounds impossible until it becomes essential. Now, when people first hear that the speed of light is the ultimate limit, the statement often arrives with a slightly futuristic glow. It sounds like something from science fiction. Starships cannot quite get there. Messages are delayed by cosmic distances. Time behaves strangely at very high speeds. All of that is true, and all of it is interesting, but there is a quieter fact underneath it that is even more important. The speed of light is not merely about light. It is about the structure of reality itself. That is the first thing to hold on to tonight. This limit is not some random regulation, applying only to bright beams and laser pointers. It is built much deeper into the world than that. Light just happens to reveal it in a particularly clear way. In fact, one of the reasons light is so central is that it forces us to confront something we usually take for granted without even noticing. We assume that motion is simple. We assume that if one thing moves faster than another, then you can just keep adding speed in the obvious way until, eventually, you get a very fast thing. Perhaps an alarmingly fast thing. Perhaps a thing moving so quickly it would make your car insurance company faint on the spot. But still, just a faster and faster thing. nature, as it turns out, disagrees. And this is where the story becomes interesting, because the disagreement is not loud. The universe does not put up a big warning sign saying do not exceed this amount of motion. There is no cosmic traffic officer waiting behind a moon, prepared to issue a citation to an electron with ambition. Instead, the rule shows itself indirectly, through the way measurements fit together, through the behavior of energy and matter, through the way fields interact, and through the stubborn refusal of experiments to support the comfortable assumptions people once made about space and time. That older comfortable picture is worth remembering for a moment, because it was not foolish. For a long time it seemed perfectly reasonable to imagine that space was just there. Time flowed the same for everyone, and motion was something you measured against a stable background. If a train moved forward and someone inside the train tossed a ball ahead, then the speed of the ball relative to the ground was just the speed of the train plus the speed of the throw. Straightforward, sensible, hard to argue with while standing on a station platform. And for many ordinary situations, that way of thinking works beautifully. The problem begins when light enters the room and refuses to behave like a tossed ball. Suppose you shine a flashlight from a moving train. Common sense, at least the old kind, suggests that the light should inherit the train motion in the same way the ball does. If the train is moving forward and the light is sent forward, then surely an outside observer should say the beam is going faster than it would from a train at rest. And yet that is not what nature allows. No matter how the source moves, and no matter how the observer moves, the measured speed of light in empty space remains the same. The full consequences of that statement are so deep that even now, after more than a century of modern physics, they still manage to unsettle people who meet them for the first time. Because think about what must give way if that is true. If the speed of light is fixed for everyone, then something else has to adjust. Space cannot remain the simple neutral stage we imagined. Time cannot remain universal and uniform in the old sense. Measurements of distance and duration have to become more subtle than they appear in everyday life. The world has to reorganize itself around a deeper consistency. And this is one reason the subject deserves a patient introduction rather than a dramatic one. It is very easy to make relativity sound like a collection of weird effects. Time slows down, length contracts, simultaneous events stop being simultaneous. These statements are accurate, but when presented as isolated curiosities, they can feel like party tricks performed by the universe for its own amusement. They are not party tricks. They are the price of consistency. They are what reality has to do in order for this deeper rule, this invariant speed, to remain true. But even that does not fully answer the question that brought us here. Why this limit? Why should there be such a speed at all? Why not a universe in which speeds can pile up forever with no final barrier? Why not a cosmos where motion is limited only by engineering, fuel, patience, and perhaps the durability of the pilot? Why does nature insist that there is a special speed woven into its laws? The answer, or at least a large part of it, lies in something that became clearer as physics moved from particles as tiny billiard balls to a more mature picture of fields, interactions, and the strange rules of the quantum world. That is where Feynman enters the story in an especially important way. Richard Feynman is often remembered as the lively explainer, the bongo player, the man with the sharp jokes and the sharper mind. All of that is part of the picture, but what matters for us tonight is not his personality, so much as the way he helped reveal how nature actually organises interactions at the deepest level we can currently describe with confidence. He did not personally invent the idea that light speed is a universal limit. That came earlier, and it came through the work of Einstein and many others. But Feynman helped uncover why the world of particles and forces fits that rule so tightly. He showed, in a way that changed physics forever, how light and matter interact through quantum fields, and why those interactions do not treat empty space as a simple, blank void. Empty space, in modern physics, is never just nothing. That may sound suspiciously like the sort of sentence designed to keep philosophy departments funded indefinitely, but in this case it is a concrete physical statement. What we call empty space is structured by fields. Particles are not little independent objects floating through a dead vacuum like crumbs in still air. They are excitations of fields, patterns of behaviour that exist within a deeper framework. Light is tied to one of those fields, electrons are tied to another, and the rules governing how those fields behave are not optional decorations. They determine what can happen, how quickly influences can travel, and what counts as a physically consistent universe. One of the beautiful things Feynman helped make usable was a way of thinking about interactions not as vague exchanges but as precise processes. An electron does not simply feel a force in some mystical fashion. It interacts through the electromagnetic field. Light is not merely illumination. Photons, the quanta of light, are part of the machinery by which electromagnetic interactions are carried. This does not mean that whenever you lean on a table, you should imagine a tiny committee of photons holding a meeting about your elbow, but it does mean that the forces shaping everyday reality are inseparable from the structure of fields and their permitted interactions. And once you see the world that way, the speed of light stops looking like a curious fact about brightness and starts looking like a boundary built into causality itself. A limit on the transmission of influence. A rule about how the fabric of physical events can connect to one another without contradiction. In a very deep sense, it is not just that light happens to move at this speed. It is that this speed is the one around which the laws of space-time and field interactions are organized. You can feel the shift there. The question changes. We stop asking why light is fast in the casual way we might ask why a car has a certain top speed. Instead, we begin asking why the universe is built so that there exists a single invariant speed, and why massless things move at it while massive things cannot. That is a much more fundamental question, and it takes us away from machines and into ontology, which is a serious-sounding word for what things really are once your first guesses have all failed. Still, there is no need to become overly solemn about it. Physics has a habit of sounding very grand while beginning with things that are almost comically plain. Look at the night sky, turn on a lamp, watch someone throw a ball, ask whether two observers moving differently should agree on what happened and when. The gap between those simple acts and the deepest structure of the universe is smaller than it seems. That is one of the most charming features of the subject. Reality leaves clues in ordinary life. They are just well hidden by the fact that ordinary life happens at speeds and scales where the strangest rules stay politely in the background. That politeness, however, has limits. Once science became precise enough, nature stopped letting the old assumptions pass unchallenged. Experiments measuring the behaviour of light refused to cooperate with the idea of a universal stationary background. Electromagnetism, as described in the 19th century, already contained a fixed speed in its bones. Einstein recognised that this was not a nuisance to explain away, but a sign that our concepts of space and time needed revision. Then, in the 20th century, quantum theory deepened the picture further, and Fineman became one of the key figures in turning that deeper picture into a practical framework for understanding how light and matter actually behave. So in the path ahead, we're going to keep two threads in view at once. One is the relativistic thread, why any limit on speed has to reshape our understanding of time, distance and motion. The other is the quantum field thread, why the deepest interactions of matter and light make this limit feel less like an arbitrary prohibition and more like an expression of how physical reality is assembled. There is also a more human thread, and I do not want to lose that one. The reason questions like this survive for generations is not just that they are technically important, it is that they bother us in a productive way. They expose the mismatch between intuition and truth. Human beings evolved in a world of falling fruit, thrown stones, and moderately paced regret. We did not evolve to think naturally about invariant speeds, field excitations, or spacetime geometry. And yet, here we are, a species that somehow climbed from campfires to particle accelerators and discovered that the universe is under no obligation to match common sense. There is something reassuring in that, oddly enough. It means confusion is not failure. It is often the correct first response. If the speed of light as a universal limit feels strange, that is because it is strange. The goal is not to pretend it is obvious. The goal is to let the strangeness become organised, to replace a vague feeling of impossibility with a clearer sense of why the impossible thing is actually the most consistent possibility available. And consistency, more than cleverness, is the real hero of this story. Physics is often presented as if progress comes from brilliant people having bold ideas in isolation. There is some truth in that. Bold ideas matter. Brilliant people help. But what decides the outcome in the end is whether the pieces fit, whether the same laws can describe many different situations without tearing themselves apart, whether observers moving differently can still agree on the underlying structure of events, whether causes remain before effects, whether field interactions stay local and coherent, whether the quantum world and the relativistic world can share the same house without setting the curtains on fire. Feynman was a master of making those pieces fit in a way that let physicists calculate real outcomes with astonishing accuracy. The interaction of light and electrons, the tiny shifts in energy levels, the scattering of particles, the corrections that arise from quantum behavior in the electromagnetic field, all of this became part of a unified framework of breathtaking success. And in that framework, the light speed limit is not a decorative slogan painted on the side. It is part of the load-bearing structure. So let us begin where all of this becomes unavoidable, with the old intuition that speed should simply add, with the first cracks that appear when light enters the picture, and with the simple but dangerous question that pushes the whole door open. What would the world have to be like if there were no ultimate speed at all? Because once you ask that carefully, and once you compare it to the world we actually observe, the need for a limit starts to emerge not as a cosmic inconvenience, but as the thing that keeps reality from becoming contradictory the moment anything tries to influence anything else at a distance. And that is where the path starts to narrow, and where the familiar idea of motion begins to give way to something much deeper. When people hear that light is the fastest thing in the universe, the sentence often lands with a kind of easy familiarity. It sounds like one of those facts everybody picks up early, somewhere between learning that the Earth goes around the sun and discovering that your school textbooks somehow managed to make both of those things feel less exciting than they really are. Light is fast, very fast, faster than anything else. We hear it so often that the claim begins to feel almost decorative, like a label attached to reality rather than a deep rule about how reality works. But the statement deserves more attention than that, because it is not merely a record in some cosmic race. It is not that the universe held a competition, invited all known phenomena to the track, and light happened to cross the line first while everything else wheezed far behind. The reason light is the fastest thing is more fundamental than that. It is not just the current winner, it represents the limit built into the structure of nature itself. That is a very different idea. In ordinary life, speed feels like the sort of property that should always admit improvement. A faster horse becomes a carriage. A faster carriage becomes a train. A faster train becomes a plane. A faster plane becomes a rocket. And if you carry that pattern forward in the lazy way the human mind often does, you start imagining that greater speed is simply a matter of better engineering, more energy, stronger materials, sharper ideas, and perhaps fewer safety regulations. There is always some higher number waiting just beyond the current one. That expectation makes sense in daily experience, because nearly everything around us lives so far below the real limit that the world lets us pretend the ladder can go on forever. Then physics clears its throat and says no. There comes a point where faster stops being a practical problem and becomes a conceptual one. The barrier is not there because our engines are weak, or our spacecraft are disappointing. It is there because motion itself is not stitched into the universe the way common sense first suggests. Light does not merely happen to be outrageously quick. Light reveals that there is a deepest speed woven into space and time, and that speed is the same for all observers in empty space. That is why the sentence matters. It's not a fact about brightness. It is a fact about the architecture of the world. One of the easiest ways to feel the strangeness of this is to compare light with other familiar things that move. Sound, for example, also travels. It can move very quickly by ordinary standards. A shout crosses a room. Thunder follows lightning from far away. Music fills a hall, but sound is not fast in the same way light is fast. Sound is a vibration passing through a medium. Air molecules nudge neighbouring molecules and the disturbance moves onward. That means the speed of sound depends on the material carrying it. In air it has one value. In water it has another. In steel it has another still. Sound is not a basic speed limit for the universe. It is the local speed of a particular kind of disturbance in a particular kind of stuff. Light is different. Light in empty space does not need air or water or anything else to carry it along. That difference alone should already make us suspicious that we're dealing with something more profound. For a long time, people hoped there might still be some hidden medium, some invisible background filling all of space through which light waves moved. That idea had a certain appeal. It preserved the old instinct that waves must be waves in something. But nature was not interested in preserving the instinct. The experiments refused to support the picture. Light did not behave as though it needed a cosmic substance beneath it. Empty space itself was enough. That phrase, empty space itself, is one of those expressions that sounds harmless until you look at it closely. Because what does that mean? How can emptiness have properties? How can it permit one particular speed and not another? How can a vacuum, which sounds like the absence of everything, turn out to be structured enough to matter so deeply? This is one of the places where modern physics quietly changes the ground beneath your feet. Empty space is not nothing in the childish sense of a blank void. It is the arena in which fields exist and interact. It has a geometry. It has rules. It is not a passive container. It is part of the physical story. That is why saying light is the fastest thing in the universe is a little like saying the horizon is the farthest part of the sea. It is true in a loose conversational way, but it misses the real point. The important thing is not that light has some unusually impressive speed in the way a cheetah has unusually impressive legs. The important thing is that the laws of nature single out a universal speed, and light, because it has no rest mass, travels at that speed in vacuum. That is why light occupies such a special place. It is not the cause of the limit, it is the clearest expression of it. This also helps correct another common misunderstanding. People sometimes imagine that light is fast because photons are somehow tiny enough, or because they are slippery, or because they do not have to push through space in the way larger things do. But that way of thinking smuggles in the wrong picture. It treats speed as if it were simply a measure of how efficiently an object overcomes resistance. In daily life, that is often a useful picture. A lighter ball is easier to throw. A more aerodynamic car cuts through the air better. A skater glides farther on smoother ice. Yet none of that gets to the heart of why light has the speed it does. A photon is not moving rapidly because it is especially streamlined. It moves at the invariant speed because that is what massless excitations of the electromagnetic field do in empty space-time. That sounds more severe than it needs to. Put more simply, the reason is not mechanical, it is structural. This is also why asking what is the fastest thing in the universe has a surprisingly delicate answer. In casual speech, the answer is light. In a deeper physical sense, the answer is that anything massless travels at the same limiting speed in vacuum. Light is the most familiar example because we encounter it constantly. It reaches us from lamps, screens, stars, and the sun. It brings us almost everything we know directly about the wider cosmos. But the underlying principle is broader than visible light. The The universe is not running a beauty contest for the electromagnetic spectrum. It is enforcing a rule about what massless entities do. Once that is clear, another question arrives almost immediately. If light is the fastest thing, why can matter not simply be pushed harder and harder until it catches up? Why should having mass make such a decisive difference? After all, in ordinary experience, adding energy makes things move faster. Roll a ball gently and it drifts. Throw it harder and it goes faster. Continue this line of thought and it seems natural to suppose that enough energy should eventually drive anything to any speed. Yet the closer matter gets to the limiting speed, the more stubborn nature becomes. Extra energy continues to change the motion, but not in the simple way intuition expects. You never quite arrive. That refusal is one of the central clues that the universe is not built on classical habits of thought. In older mechanics, speed looks open-ended. In relativistic physics, speed lives inside a geometry with a boundary built into it. Massive objects can move ever closer to the limit, but the structure of space-time prevents them from reaching it. Massless ones do not gradually work their way up to it. They simply travel at it. The distinction is not a matter of effort. It is a matter of category. To make this feel less like a technical decree from an unfriendly textbook, it helps to remember how invisible the issue normally is. Human life unfolds at slow speeds by cosmic standards. Even high-performance aircraft, fast particles in ordinary devices, and planets in motion are operating well below the limit where relativity begins to slap the table and insist on being noticed. That is why the classical picture survived so comfortably for so long. It is a good approximation in the range that evolution gave us. If our ancestors had spent their afternoons hurling near-light speed fruit at one another, our intuitions might be very different. They did not. They had other concerns. So common sense, admirable in many situations, enters this subject with a disadvantage. It wants velocity to behave like money. If you have some and I give you more, you now have the combined total. It wants time to tick the same way everywhere. It wants distance to be agreed upon by all reasonable people. It wants simultaneity to be obvious. Light speed wrecks all of those comforts at once. If every observer measures the same speed for light in vacuum, then space and time cannot remain the rigid universal stage they first appeared to be. They must adjust. Durations can differ between observers. Lengths can differ. Two events that seem simultaneous in one frame need not be simultaneous in another. These are not optional oddities added to make relativity sound dramatic. They are the consequences required to keep the invariant speed truly invariant. And that brings us back to why light is the fastest thing. It is because the universe needs a consistent speed for causal structure. There must be a boundary separating events that can influence one another from events that cannot do so immediately. Without such a boundary, the ordering of cause and effect becomes unstable. Different observers could disagree in ways that would not merely be surprising but contradictory. One observer could treat a signal as arriving before it was sent. The logic of physical interaction would begin to fray. The limiting speed is not just about motion. It is about preserving the consistency of causation across the structure of space-time. That phrase, preserving the consistency of causation, is the sort of thing physicists say with straight faces, and it is worth translating into ordinary language. The universe must have rules for what can affect what, and in what order. If no upper limit existed for the propagation of influence, then the relation between events would depend too loosely on the observer. Reality would lose the stable scaffolding required for a shared physical world. The light speed limit is therefore not a nuisance placed in front of ambitious spacecraft designers. It is part of the mechanism by which the universe stays logically coherent. This is why the fastest thing in the universe is not really a thing in the everyday sense. It is a boundary condition of reality made visible through light. There is also a psychological side to this that I find oddly comforting. Human beings tend to mistrust limits until we understand what they're doing there. A limit feels restrictive. It sounds like bad news. But many limits are actually what make meaningful structure possible. A melody needs constraints or it dissolves into noise. A language needs grammar, or it becomes a blur of sounds. A game needs rules, or it stops being a game and becomes an argument. The speed limit built into the universe functions in something like that way. It restricts, yes, but it also stabilizes. It gives space-time a consistent causal order. It allows fields and particles to interact without plunging physics into contradiction. Now, none of this means light is simple, quite the opposite. The more closely science examines light, the more trouble it caused for old ideas. It behaved like a wave, then also like a particle, then like something better described by quantum fields than by either naive picture on its own. It could interfere with itself, arrive in discrete quanta, and mediate electromagnetic interactions. It became, in a sense, a guide into the modern view of nature. Light was not just one phenomenon among others. It was a teacher, though not a particularly patient one. That is where someone like Feynman becomes important later in our journey. Once the relativistic lesson had been learned, physics still had to understand how light and matter actually interact at the quantum level. This was not a decorative afterthought. It was essential. It is one thing to say that the universe has a limiting speed. It is another to build a theory in which charged particles, photons, and the vacuum itself behave in a mathematically consistent way while respecting that limit. Feynman helped transform that challenge into a workable framework. His methods did not merely describe particles as isolated little objects bumping about. They revealed interaction as something encoded in fields and amplitudes, constrained by both quantum principles and relativity. But before we get there, it is worth staying a little longer with the apparently simple claim in front of us. Light is the fastest thing in the universe. Try saying it again, but with less casualness this time. Light marks the maximum speed at which information, influence, and causal connection can travel through empty space. Light is not just quick. Light sits on the edge of what spacetime permits. Light is what a massless field excitation looks like when the universe enforces its deepest speed rule. That's a very different sentence hiding inside the familiar one. It also helps explain why stories about faster-than-light travel are so intoxicating. They do not merely offer a quicker route to another star. They tempt us with escape from one of the foundational constraints of physical reality. The fantasy is not just convenience, it is rebellion against structure. And perhaps that is why such stories persist. They take a real limit and ask what it would mean to slip around it. Science fiction has every right to ask that question. Physics, less romantically, must then answer that under known laws the cost of such rebellion is severe. Once faster-than-light influence enters the picture, the neat order of cause and effect begins to wobble in ways that are very hard to repair. There is another subtle point hidden here as well. When we say nothing can go faster than light, we do not mean that the universe carefully measures every moving object against some glowing beam and blows a whistle if anything gets ahead. The speed of light is not a local race official. It is the numerical expression of a deeper invariant built into space-time. Massive objects follow one kind of path through that structure. Massless ones follow another. The rule is not imposed from outside. It arises from the geometry and the field laws themselves. This is one reason the subject becomes clearer, not murkier, when you stop treating space as an empty container and start treating space-time as part of the physics. The old image of objects moving through a passive background makes the limit seem arbitrary. The newer image makes it inevitable. Once space and time are linked, once observers do not share one universal clock, once causality must remain consistent, and once field interactions must respect locality, the existence of a limiting speed begins to look less like a mystery and more like a necessity. Not, of course, a necessity that feels obvious on first contact. The first encounter is usually more like polite confusion, and that is perfectly appropriate. The best ideas in physics are often the ones that feel wrong until they explain too much to be dismissed. Light as the fastest thing in the universe belongs in that category. It sounds at first like a curious fact, Then it becomes a challenge to common sense. Then it becomes a guide to relativity. Then it becomes a statement about causality, fields, and the very possibility of consistent physics. So when people say light is the fastest thing, I think it is worth pausing before nodding and moving on. The phrase is doing a lot of work. It is telling you that nature has a built-in speed that does not depend on the motion of the source. It is telling you that massless entities travel at that speed, and massive ones do not. It is telling you that time and distance are not fixed in the old absolute way. It is telling you that causal influence has a boundary. And more quietly, it is preparing you for the deeper question that follows immediately after. If this speed limit is so fundamental, then what exactly forced the universe to organize itself that way? And what did later physics, especially the work that grew around light, electrons, and quantum fields, reveal about why the limit is not merely tolerated by nature but required by it? That is the point where the story becomes even more interesting. Because once light stops being just the fastest traveller and starts becoming the messenger of a deeper rule, we have to ask why the rule exists at all, why mass changes the game so completely, and why the vacuum, which sounds like the emptiest thing imaginable, turns out to be structured enough to make the whole arrangement unavoidable. The natural next question is the uncomfortable one. It is not enough to say that light is the fastest thing. It is not even enough to say that the universe has a built-in maximum speed. Those are descriptions. They tell us what happens. But the mind keeps pushing one step further and asks why there should be any limit at all. Why did nature choose this arrangement instead of some other one? Why is the universe built so that influence cannot move arbitrarily fast? That question matters because at first glance a speed limit seems unnecessary. If you grow up with ordinary experience as your guide, nothing about motion suggests a hard boundary. Things can move slowly or quickly. With enough force they move faster. With more energy they move faster still. Common sense keeps extending the pattern. It has no obvious reason to stop. In that older picture, a speed limit looks like a strange extra rule pasted on top of an otherwise simple system. But the deeper you go into physics, the more that impression flips around. The limit does not look like an extra rule. It starts to look like the thing that prevents the whole structure from collapsing into contradictions. In other words, nature did not decide on a limit in the sense that someone might decide to lower the speed on a road because the drivers are getting reckless. It is not that the universe first had motion and then later added a warning sign. The limit is part of what makes motion, space, time, and cause and effect fit together in a consistent way. One good place to begin is with something very ordinary. Imagine one event affecting another. You flip a switch and a lamp turns on. You clap your hands and someone across the room hears it. You send a message and eventually it arrives. Everyday life is full of chains like this. One thing happens, then another follows. We do not usually think about it very deeply because the pattern seems so obvious. Causes come before effects. Information takes time to travel. Different places are linked by processes that unfold in sequence. It is easy to overlook how much structure is packed into that simple picture. Now imagine a universe with no upper limit on the speed of influence. Not just faster signals than light, but no built-in maximum at all. At first that sounds convenient. It sounds efficient. You could send information instantly across any distance. Events far apart could coordinate without delay. The cosmos would become wonderfully responsive. Yet the trouble begins almost immediately, because once you remove any limiting speed, you also weaken the structure that keeps cause and effect in order for all observers. This is where the issue becomes more than a question about engineering or travel time. It becomes a question about whether reality can remain self-consistent. In everyday life, we treat the order of events as stable and shared. If the kettle boils before the tea is poured, then everyone agrees on that order. If a glass falls before it breaks, then the sequence is not up for debate. But relativity teaches that the ordering of events at different locations is not as absolute as it first appears. Different observers moving relative to one another do not always slice time into the same set of simultaneous moments. That sounds odd the first time you hear it, but it is not a technical trick. It is one of the central consequences of having a universal speed limit, and this is exactly the point. The limit allows different observers to have different measurements, while still preserving a stable causal structure. There is enough flexibility for time and distance to adjust, but not so much flexibility that one observer can see an effect happen before its cause in a physically meaningful way. The speed limit protects the order of influence. It draws a boundary around what events can be connected by a cause and effect relation. If that boundary did not exist, or if influences could race past it freely, then some observers would be able to describe the order of events in ways that would not merely be different but contradictory. A signal could be received before it was sent. A response could arrive before the question. The idea of physical explanation would begin to come apart. You would no longer have a shared framework for saying what produced what, and once that happens, physics stops being physics in the normal sense. It becomes a tangle of incompatible histories. This is why the speed limit is tied so closely to causality. It is not just about motion, it is about preserving the possibility of a coherent universe. That may still sound a bit formal, so let's make it feel more concrete. Think about what science is always trying to do. It tries to connect events. It asks what led to what. It builds chains of explanation. This particle scattered because that field acted on it. This star shines because fusion occurs in its core. This detector clicked because something arrived and triggered it. Every explanation assumes that the world has a reliable causal order. Not always a simple one, not always an intuitive one, but a stable one. The limit on the speed of influence is part of what gives that order its backbone. There is another reason nature needs a limit, and this one comes from the structure of fields. Modern physics does not describe the world as a collection of isolated little objects moving through a dead void. It describes the world in terms of fields spread through space and time, with particles appearing as excitations of those fields. That may sound like a more abstract view, but in practice it is the one that works. Electromagnetic phenomena are not messages passed by invisible hands between separate objects. They are governed by the behaviour of the electromagnetic field. Matter itself is also tied to fields. Interactions are local. Things affect nearby things, and those effects propagate outward in lawful ways. That local character matters a great deal. Physics does not like action with no mediation and no delay. It prefers processes. Changes spread through fields. Disturbances move outward. Information is carried, not magically imposed at a distance all at once. Once you view the universe that way, a limiting speed becomes far less surprising. In fact, it would be more surprising if no such limit existed. A field-based world naturally raises the question of how fast disturbances in the field can propagate, and the answer turns out to be deeply linked to the geometry of spacetime itself. This was already beginning to appear in the 19th century, before relativity had fully arrived. Electromagnetism, in its mature classical form, did not describe electric and magnetic effects as instant influences. It described them as changes in a field that travel, and when physicists examined the equations carefully, a very particular speed appeared. It was not inserted by hand to make the math dramatic. It emerged from the structure of the theory. That speed matched the measured speed of the light. The conclusion was extraordinary. Light was not some separate mysterious substance. It was an electromagnetic wave, and the speed associated with the electromagnetic field was a built-in property of the theory. That discovery was one of the great hints that nature had already chosen a limit long before physicists understood the full consequences. The clue was sitting there in the laws of electromagnetism, waiting for someone to take it seriously. Einstein did take it seriously. He recognized that if the laws of physics are to have the same form for observers in uniform motion, and if the speed emerging from electromagnetism is the same for all of them, then space and time cannot behave in the old absolute way. Something had to give. What gave was not the speed of light. What gave was the classical picture of time and space. This is a useful moment to notice how often human intuition backs the wrong horse. Faced with a conflict between old common sense and a new physical law, it is tempting to assume the new law must be adjusted. Surely the measured speed of a light should depend on the motion of the source or the observer in the obvious way. Surely that would be the simple fix. But nature refused the fix. The experiments kept pointing back to the same answer. The invariant speed stayed. So physics had to rebuild its understanding of time, length, simultaneity, and motion around that fact. And once that rebuilding happened, the existence of the limit no longer looked arbitrary, it looked necessary. Space-time itself came equipped with a causal structure. There are events that can influence one another through signals moving at or below the limiting speed, and there are events that cannot. The boundary is not cosmetic, it is part of the definition of what the space-time geometry permits. You can think of it this way. In a universe without such a structure, there would be no clean distinction between what is causally reachable and what is not. Everything could in principle affect everything else immediately, or in inconsistent orders depending on who was watching. That may sound liberating if your main goal is to skip traffic between stars, but it is a poor foundation for a lawful universe. Another piece of the answer comes from energy and matter. In the classical mindset, more energy always means more speed in the straightforward way. Relativity changes that. As an object with mass is pushed faster and faster, the relationship between added energy and added speed stops behaving like common sense expects. The closer you get to the limiting speed, the more resistant the motion becomes to further increase. This is not because matter becomes stubborn out of spite, it is because the geometry of space-time and the way energy and momentum fit into that geometry leave no room for a massive object to cross into the massless category. The boundary is built into the structure of the theory. That point is easy to miss if you think only in terms of force and acceleration. You might imagine that the limit is a practical matter, like a machine overheating before it reaches its maximum setting. But the real issue is not practical. It is categorical. Massive and massless entities do not simply occupy different places on one sliding scale of speed. They inhabit different kinds of motion allowed by the underlying geometry. The limiting speed marks the separation between them. So when we ask why nature decided on a limit, the answer is beginning to take shape. Nature needs a limit because influences must propagate in a way that preserves causal order. Fields must transmit changes locally rather than by unrestricted instant reach. The geometry of space-time must be consistent for all observers. Massive and massless motion must fit into a single lawful framework. The limit is what makes those demands compatible with one another. There is also a deeper lesson hiding underneath all this. Physics often advances by discovering that something we treated as independent is actually linked to something else. Space and time were once treated as separate backgrounds. Relativity linked them. Particles were once treated as independent little bits of matter. Field theory linked them to deeper structures. Causality, motion, and geometry might once have seemed like separate topics. The light speed limit reveals that they are entangled. You do not get to change one without changing the others. This is one reason the subject became even richer when quantum theory entered the story. Classical relativity already gave a strong answer to why a limit is needed, but quantum field theory tightened the picture. In that framework, fields are not just classical continuous substances, they are quantum objects with fluctuations, excitations, and strict rules about how interactions occur. Signals and influences do not leap across the universe without regard for locality. The theory is built so that physically meaningful effects respect the causal structure imposed by relativity. That harmony was not easy to achieve. It took decades of effort, failed attempts, and conceptual cleaning before the pieces sat together properly. Feynman became one of the major figures in that cleanup. His diagrams, his way of organizing interactions, and his broader work in quantum electrodynamics helped make it possible to calculate how light and matter affect one another with astonishing precision. That success was not just a matter of clever bookkeeping. It was evidence that the universe really does permit a description in which quantum processes and relativistic causality can live together. The limiting speed is one of the conditions that description must respect at every step. There is something almost amusing about this. The universe looks relaxed from far away. Stars drift, light travels, apples fall, people lose their keys. Yet under that calm surface, the rules are extremely strict. They do not allow causal disorder. They do not allow unrestricted speeds. They do not allow interactions to ignore the local structure of fields and space-time. Reality is less like a casual improvisation, and more like a system that will tolerate enormous variety only so long as its deepest consistency conditions remain untouched. That is not bad news. In fact, it is the reason science works at all. If the universe had no such discipline, we would not be able to build stable explanations. A lawful world needs constraints. The speed limit is one of the most important of them. At this point, it is worth answering a small but natural objection. Someone might say that all of this explains why a limit is useful, but not why it has the particular value it does. Why this speed rather than another one? That is an excellent question, and it takes us toward the constants built into the laws of nature. At present, physics can tell us how this speed functions in the structure of space-time and field theory. It can show that once the laws take the form they do, this invariant speed is central. What it cannot yet do in any final sense is explain from some deeper completed theory why the universe has exactly the full set of constants it has, and not some different set. So honesty matters here. We can explain why a limit is necessary within our best theories, and why the limit has the role it has. Explaining why reality has this full architecture at the deepest possible level is still an open project. That kind of partial answer is common in physics. We often learn that a thing is not arbitrary even before we can explain why the whole system exists in exactly its current form. It is still major progress. The speed limit is not a random quirk. It is part of a coherent framework that ties together relativity, electromagnetism, quantum fields, and causal structure. That is already a profound discovery. It also changes the emotional feel of the subject. A speed limit sounds restrictive if you meet it too quickly. It sounds like the universe saying no. But after a while it begins to sound more like the universe saying, this is how a lawful world is held together. This is how different observers can disagree about measurements without disagreeing about reality itself. This is how local interactions remain local. This is how signals travel. This is how causes stay ahead of effects in every physically meaningful account. The limit is not a bureaucratic annoyance, it is a structural necessity. And once you see it that way, the next step becomes unavoidable. If the universe enforces a limit because space-time itself is built around this invariant speed, then we have to look more closely at what Einstein realized. We have to see exactly how the old picture of motion fails, why chasing light leads to paradox, and why the barrier is not an engineering obstacle at the edge of a racetrack, but something much deeper built into the geometry of reality itself. To see why the limit on speed is not just a rule, but a real boundary built into nature, it helps to spend some time with the problem that forced Einstein to rethink motion itself. Before relativity, people had a picture of the world that felt very stable. Space was just there, like a stage. Time flowed the same way everywhere, for everyone, whether they were standing still, riding in a train, or sailing through interplanetary emptiness, which would have made train schedules easier and physics less interesting. Motion took place against that background. If something moved, it moved through space over time, and those two ingredients were treated as separate and absolute. It was a clean arrangement. It also turned out to be wrong. The trouble appeared when physicists tried to take light seriously on its own terms, not as a loose everyday phenomenon, not as something you use to find your slippers in the dark, but as a physical process governed by laws that had been written down with increasing precision. Those laws did not behave as if light were just another moving object. They did not say that the speed of a light should depend on the motion of the source in the ordinary way. Instead, they pointed to a single fixed speed. That was not merely inconvenient, It was explosive. Because if light really had the same speed for all observers moving uniformly, then the old picture of space and time could not remain intact. Einstein saw this more clearly than almost anyone else. He was not the only person thinking about these issues, and history is never as tidy as the popular version likes to pretend. But he made the decisive step. He stopped trying to rescue the old framework and asked what would happen if the speed of light really were fundamental. What if the laws of physics looked the same for all observers moving at constant speed relative to one another? And what if the speed of light in empty space were the same for all of them as well? Those two ideas, taken together, seem innocent when stated quickly. They are not innocent at all. They force reality to reorganize itself. One reason the old picture felt so convincing is that it works beautifully for the speeds we encounter in daily life. If you walk forward inside a moving train, a person standing outside sees you moving faster than the train alone. If you toss a ball forward from the front of a boat, someone watching from the shore adds the speed of the throw to the speed of the boat. This is not a bad theory of motion. It is a very good approximation for ordinary experience. But it is not universal. Light refuses to follow the same rule. Shine a flashlight from a moving train and the person on the embankment does not measure the beam as travelling at the train speed plus the light speed. They still measure the same light speed. The same is true even if the source is moving in the opposite direction, or if the observer is moving. The measured speed of light in vacuum remains the same. That simple statement is the wall at the edge of motion. It is called a wall not because it is a physical surface waiting somewhere in front of a spaceship, but because once you begin approaching it, the entire structure of motion starts to behave differently. The old arithmetic of speed stops working. Time and distance no longer sit quietly in the background. They begin to shift in just the ways required to preserve the invariant speed. The wall is not a brick barrier. It is a change in the rules by which reality measures movement. You can feel how radical this is by asking a childish-sounding question that turns out to be extremely dangerous. Dangerous to old physics, at least. What does light look like if you run alongside it? In the 19th century, that question was already haunting thoughtful physicists. If light is a wave, and if you move fast enough in the same direction, then perhaps you should eventually be able to keep pace with the wave. You might imagine seeing a frozen ripple in space, a stationary light wave hanging there. But the laws of electromagnetism do not allow such a thing. There is no physically sensible state in which an observer moving uniformly alongside a light wave sees a frozen electromagnetic pattern of that kind. The mathematics resists it. Nature resists it. The old idea of simply catching up and matching pace with light leads to nonsense. Einstein took that resistance seriously. He did not patch it with an excuse. He concluded that the familiar notions of time and simultaneity had to change. This is one of the most important intellectual moves in science. Instead of forcing the new evidence into the old concepts, he rebuilt the concepts themselves. Simultaneity is the hidden hinge in all of this. In ordinary life, it feels obvious what it means for two events to happen at the same time. 2 lamps flash, 2 doors close, 2 bells ring. If you're nearby, you just look and decide. But once distances become large and signals travel at finite speed, that easy confidence starts to wobble. How do you decide whether distant events were truly simultaneous, rather than merely observed together after light from them reached you? To answer that, you need a method for synchronizing clocks at different places, and the moment you use light signals to do it, the structure of the problem changes. The synchronization depends on the speed of light, and if that speed is invariant for all observers, then different observers in relative motion do not agree on which distant events count as simultaneous. That is not a side effect, it is central. The old world assumed one universal present, a shared now slicing cleanly across the universe. Relativity removes that comfort. There is no single global now that all observers in relative motion must share. Each observer has a valid way of dividing events into past, present and future relative to their frame of motion. But these divisions do not line up in the absolute way common sense expected. This sounds like philosophy until you realise it has direct physical consequences. If observers disagree about simultaneity, then they will also disagree about lengths and durations, because length depends on measuring the positions of endpoints at the same time, and duration depends on comparing clock readings. Once simultaneity becomes frame-dependent, so do these other quantities. This is why time can dilate and lengths can contract. These are not mysterious distortions caused by speed, as though motion itself were bending clocks out of spite. They are the consistent consequences of a space-time structure built around an invariant speed, and this is where the wall becomes visible. It is not visible because you hit some glowing border. It is visible because the closer you push a massive object toward that limiting speed, the more pronounced these relativistic effects become. Time intervals measured in different frames diverge more strongly. Distances along the direction of motion are not agreed upon in the old way. The relation between energy and speed becomes increasingly unforgiving. You can keep adding energy, but the speed gains become smaller and smaller as you approach the limit. The wall is built into the geometry of the approach itself. It helps to avoid a common misunderstanding here. People sometimes imagine that the wall exists because matter gets heavier in a simple mechanical sense, and eventually becomes too hard to push. That old style explanation can be misleading. The more careful way to think about it is that the geometry of space-time determines the allowed motions of objects with mass. Massive objects always move through space-time in a way that keeps them below the invariant speed. Massless entities follow a different kind of path, one that lies exactly on that limit. The distinction is not a matter of trying harder. It is a matter of what sort of thing the object is within the structure of the theory. This is why the wall is so strange. In ordinary life, barriers feel external. A wall blocks you because it is made of material and you run into it. A mountain blocks your car because the road does not go through it. A locked door blocks you because someone had trust issues and bought good hardware. But Einstein wall is not external. It is internal to the logic of space-time. You do not collide with it. You asymptotically approach it and never arrive, because the rules governing time, length, energy and causality do not permit the crossing. One of the cleanest ways to understand how severe the old picture fails is to think again about adding velocities. In classical motion, if one object moves relative to a second and the second moves relative to a third, you just add the speeds. This works well when all speeds involved are small compared with the limit. But if you use that rule carelessly with light, you immediately get into trouble. If a beam of light leaves a fast-moving spacecraft, the classical rule would predict that different observers could measure different light speeds depending on the spacecraft motion. But that is not what experiments show, and not what electromagnetism predicts. Relativity repairs the situation by replacing the old addition rule with a new one that preserves the invariant speed. Speeds still combine, but not in the naive way. The closer the values get to the limit, the more the relativistic structure matters. That change is not some mathematical luxury. It is the price of consistency. Once you accept that light speed is invariant, you must accept that motion itself has to be described differently. Einstein did not put up the wall because he liked complications. He found the wall because the universe demanded it. There is another part of the story that deserves emphasis. The wall is not just about preventing matter from becoming too fast, it is also about preserving a stable causal order. If it were possible for material objects or signals carrying information to move faster than the invariant speed, then the ordering of cause and effect could become observer, dependent in dangerous ways. Different frames of motion could disagree not merely about timing details but about which event influenced which. A reply could arrive before the message that prompted it. An alarm could ring before the event it was meant to warn about. Physics would become deeply unstable. The wall protects the order of influence. This is why relativity is not a theory of weird clock behavior. It is a theory of space-time with a built-in causal structure. The limit on speed marks the boundary between what can affect what in a lawful way. Events inside that causal reach can be connected by signals or material processes. Events outside it cannot be linked without violating the structure that keeps cause ahead of effect. The wall is therefore both a kinematic boundary and a logical one. It defines the possible routes by which the world can hang together. You might wonder why this was so hard for people to accept. In hindsight, it can look almost inevitable. Once the clues are assembled, once the experiments are known, once the mathematics is clear, the answer seems clean. But accepting it required giving up some of the most stubborn intuitions human beings possess. We like universal time because it feels simple. We like absolute simultaneity because it matches direct experience at low speed. We like the idea that faster is just more of the same. Relativity tells us that all three instincts fail when examined carefully enough. That is asking a lot from intuition. There is also something psychologically odd about a wall you can never touch. We are used to limits that announce themselves with impact. Touch a stove and you learn about heat in a very memorable way. Drive into a ditch and the road geometry becomes suddenly important. But the relativistic wall does not show itself like that. It reveals itself through measurement, through consistency, through the behaviour of clocks, particles and signals. That makes it both more subtle and more profound. It is not one obstacle among others. It is a hidden structural boundary that everything must obey whether or not human senses notice it directly. As physics developed, this wall only became more central. It was not some temporary correction later replaced by a better picture. Instead, it was absorbed into deeper theories. The geometry of space-time, the behaviour of electromagnetic fields, the causal structure of relativistic field theories, and later the quantum description of particles and interactions all had to respect the same limit. This is one reason Einstein's work did not merely solve a puzzle about light. It changed the language in which later physics had to be written, and yet it is important not to mythologize Einstein in the wrong way. He did not simply invent an arbitrary barrier at the edge of motion by pure imagination. He recognized a conflict in existing physics and pursued it honestly. The speed of light appeared fixed. The laws of physics ought to hold equally for uniformly moving observers. If both were true, then the old absolute framework had to go. The wall emerged from that decision. It was discovered by taking known principles seriously, not imposed like a dramatic plot twist. The more you think about it, the more impressive that is. Plenty of people can accept a surprising result after the fact. Far fewer are willing to question the hidden assumptions that make the old result feel natural in the first place. Einstein questioned those assumptions. He asked what time really means when measured by clocks in relative motion. He asked what simultaneity really means when signals travel at finite speed. He asked what motion itself means in a world where light does not let itself be treated like a thrown stone. Those questions expose the wall. Once the wall is there, many later results stop feeling like disconnected oddities. Time dilation is no longer an isolated curiosity. It is part of the structure needed for observers to agree on the invariant speed. Length contraction is no longer a bizarre squeezing of objects by motion. It is a frame-dependent measurement effect tied to the relativity of simultaneity. The inability of massive objects to reach light speed is no longer a practical failure of propulsion. It is built into the geometry of allowed motion. The wall unifies all of these. It also changes how we think about the word motion itself. Before relativity, motion was something that happened in time and space. After relativity, motion is better understood as a path through space-time. That sounds like a modest change in vocabulary, but it is much more than that. It means an object is not simply moving through space while time ticks elsewhere as an independent backdrop. Its path through space-time is the fundamental thing, and different observers decompose that path into space and time in different ways depending on their motion. Once you see that, the wall makes sense. The invariant speed is part of the geometry that constrains those paths. This also explains why light occupies such a special role. Light does not merely move very fast through space-time. It follows the boundary case built into the structure. It traces the limit that separates different causal regions. In that sense, light is not just the fastest traveller, it is the visible marker of the edge itself. There is a wonderfully stern elegance in that. The universe does not leave the limit vague. It provides a phenomenon that constantly displays it. Every star, every lamp, every distant galaxy, every reflection on a window at night is quietly participating in the same fundamental rule. Light keeps reminding us that the world is not built on our first guesses. And that leads naturally to the next step, because once Einstein wall is in place, one question becomes unavoidable. What would it even mean to try to chase light itself? Not just in the loose science fiction sense of building a faster ship, but in the careful physical sense. What would an observer experience if they tried to run alongside a beam? And why does the very attempt reveal the failure of classical thinking so completely? That is where the paradox becomes sharp enough to force the issue, and where the difference between ordinary motion and the motion of light stops being a technical detail and becomes the key to the whole story. There is a reason the question stayed with Einstein for so long, because it sounds so innocent at first. What would it be like to chase a beam of light? Not to admire it from across a room, not to study it from the safety of a laboratory bench, but to imagine yourself moving faster and faster in the same direction until somehow you draw level with it. It is the sort of question that almost feels like a child asking it, and that is often how important questions arrive. Not dressed in technical language, not carrying a notebook, just a simple picture that seems harmless until it starts breaking the furniture of your worldview. At first glance, the idea seems perfectly sensible. If you can run beside a bicycle and drive beside a train, then why not fly beside a beam of light? If motion is just motion, then enough speed should let you catch up to anything. The logic feels straightforward. Light moves forward. You move forward. You keep increasing your speed. Eventually you should be moving alongside the beam, and if that happened, you might expect something very strange but still comprehensible. Perhaps the light wave would appear frozen next to you, as if its ripples were suspended in space, no longer moving past. It would be a stationary pattern, a wave that somehow stood still. That picture is deeply tempting because it follows the habits of ordinary life. When you match the speed of another moving thing, relative to you, it stops advancing. A car beside you on the motorway appears almost still for a moment. A runner matching your pace on a track can seem frozen against the background. The same thought seems as though it should apply to light, and yet it does not. This is the point where the question stops being cute and starts becoming explosive. A frozen light wave is not something the known laws of electromagnetism permit. Light, in the classical picture that existed before relativity fully changed the rules, is an oscillation of electric and magnetic fields. Those fields do not admit a simple stationary ripple in empty space of the kind this thought experiment seems to demand. The theory did not contain such a state. If you tried to chase light and match its speed in the old framework, you would be asking nature to produce an electromagnetic pattern that the laws themselves did not know how to support. That was the first crack. Not a crack in light, but a crack in the assumptions we were using to talk about motion. Because if ordinary velocity addition were correct in the fully universal sense, then one observer ought to be able to ride alongside a beam and see it standing still. But if the equations describing light do not allow that, then something has gone wrong in the way we are combining the ideas. You can respond to that conflict in two broad ways. You can try to rescue the older picture by inventing hidden complications, or you can accept that the older picture itself is the problem. Einstein eventually took the second path. To appreciate how radical that was, it helps to stay with the thought experiment a little longer. Imagine you're in a spacecraft moving through empty space. Ahead of you, in the direction of travel, a beam of light is emitted. As you increase your speed, common sense says the light should appear to move away from you more slowly. That is what would happen with almost anything else. If you chase a thrown ball, the ball gains on you less quickly than it would if you stood still. If you move toward a drifting cloud, it takes less time to reach it than if you remain on the ground. Relative speed appears to shrink as your own speed increases in the same direction. So the naive conclusion seems irresistible. Get fast enough and the light should almost hover. Get faster still and perhaps it should hover exactly. But relativity says no. No matter how fast your spacecraft moves, so long as it moves below the invariant speed as all massive objects must, you still measure light in empty space moving away from you at the same speed. Not almost the same, not nearly the same, the same. That is not merely odd, it is a total refusal of the old intuition. The moment you accept that refusal, you are forced into a different understanding of what an observer is allowed to measure. The problem is not with the beam. The problem is with the expectation that time and space remain fixed and universal, while speeds are added in the old way. They do not. If every inertial observer measures the same light speed, then the observers must disagree about other things instead. They must disagree about how much time passes between events. They must disagree about the lengths of moving objects. They must disagree about which distant events count as simultaneous. The world has to reorganize the bookkeeping so that the speed of light stays invariant. That is why chasing light is such a powerful thought experiment. It exposes the hidden assumptions all at once. You begin with a very ordinary idea about catching up. Then, as soon as you apply it to light, everything unravels. The old way of combining motion leads you toward a stationary wave that physics does not allow. The only escape is to stop treating time and space as absolute. This is also why the question has such a peculiar emotional force. It sounds like a problem about going very fast, but it is really a problem about the meaning of motion itself. The temptation is to imagine speed as something layered on top of an otherwise stable universe. Things are what they are, then they move faster or slower through a fixed background. Chasing light shows that this is too simple. Motion is not happening inside an untouched container. The measurements of space and time depend on the motion of the observer. The background is part of the physics. There is another subtle point here. When people picture chasing a beam of light, they often imagine the beam as a little object or packet running ahead like a rabbit on a track. You speed up, it speeds away, and the only question is whether you can close the gap. But light is not best understood in that cartoonish way. Even in the classical picture, it is a wave in the electromagnetic field. In the later quantum picture, it is tied to photons, and the electromagnetic field more deeply still. Either way, it is not just a tiny bead zipping through empty nothingness. It is part of a field-based structure of reality, and that structure already knows about the invariant speed. So the idea of catching light by simple pursuit turns out to be based on the wrong mental model from the start. This becomes even clearer when you ask what your own frame of reference would have to be if you were actually moving with the beam. In classical thinking, every speed ought to correspond to a possible rest frame. If a train moves at one speed and a car at another, there is a frame in which each is at rest. So if light moves at some speed, the old instinct says there should also be a frame in which light is at rest, yet there is no such frame. Light does not possess a valid rest frame in the way massive objects do. The attempt to assign one is precisely what fails. That failure is not a missing convenience. It tells you something profound about the categories nature uses. Massive objects can be at rest in some inertial frame. They can move slowly, more quickly, or very quickly relative to different observers, but there is always some frame in which they are not moving spatially at all. Light is not like that. It is not the sort of thing that can be brought to rest by changing viewpoint. It always lies on the boundary defined by the invariant speed. That is why you cannot catch it in the everyday sense. There is no observer frame that turns a light beam into an ordinary stationary object. And notice how strange this is when you compare it with daily intuition. We're used to thinking that differences between observers are just perspective changes layered onto one shared physical reality. One person is moving, another is still. but surely the underlying objects are the same objects doing the same thing. Relativity keeps the shared reality, but alters the structure of the measurements. Different inertial observers are not just taking casual looks from different angles. They are making measurements using clocks and rulers that are related through space-time in a way our low-speed instincts never prepared us for. Chasing light lays bare the cost of ignoring that. It also helps explain why the speed of light should not be treated as just a very high number. If it were merely a large speed like any other, then in principle you ought to be able to match it by piling on enough velocity. The fact that you cannot is what makes it special. Light speed is not just quantitatively extreme, it is qualitatively different. It marks a boundary in the structure of possible motion. Try approaching the problem from another angle. Suppose you did somehow manage to move alongside a light beam. What would happen to the oscillation of the electric and magnetic fields that constitute the beam in the classical description? If the wave were frozen relative to you, those fields would vary in space but not in time. Yet the laws of electromagnetism, as they were known, do not give a free-travelling light wave that simply becomes a static ripple in empty space by changing observer. The possibility is not sitting there waiting to be discovered by a sufficiently athletic astronaut. It is absent. The theory itself rejects the picture. That rejection is one of the signs that the classical transformation rules between moving observers cannot be right for light. This is why Einstein did not merely ask how to catch light. He asked what the attempt reveals about the world. He saw that the contradiction was not a local quirk but a global warning. If the laws of electromagnetism hold, and if no observer can ever see a frozen light wave by riding alongside it, then the transformation from one inertial frame to another cannot preserve the old assumptions about absolute time and simple velocity addition. A new spacetime structure is required. Once that new structure is in place, the problem dissolves in a remarkable way. You no longer expect there to be a rest frame for light, because light-like motion is fundamentally different from time-like motion. A massive observer can approach the invariant speed but never reach it. A massless entity does not climb up to that speed from below. It exists on that boundary from the outset. The gap between you and a beam of light is therefore not just a difference in how much velocity each has accumulated, it is a difference in the kind of path each can take through space-time. That last point matters because it prevents a very common misunderstanding. Many people imagine that if you keep accelerating forever, you should eventually pass through all possible speeds in order, including the speed of light itself. That would be true in a world where speed were just a linear ladder with no structural change at the top. But relativistic motion is not like that. As you add more and more energy to a massive object, its speed relative to the invariant limit changes more and more reluctantly. The object does not march toward the limit with steady steps, it approaches asymptotically. The closer it gets, the more the structure of spacetime resists the classical picture of further simple gains. Chasing light becomes a pursuit with no final capture. There is something almost philosophical in this, but it is not empty philosophy. It is hard physics presented through a very human desire to imagine ourselves in another reference frame. What would I see if I moved with the beam? The answer is that the question itself breaks the classical rules and forces a better one. You cannot ask for the view from a light rest frame because no such inertial frame exists. The request is like asking for the north of the North Pole. The phrase sounds grammatically valid, but the geometry beneath it refuses to cooperate. That is one of the reasons this thought experiment remains so useful even now. It teaches by failure. It starts from a natural assumption, pushes it until it breaks, and then leaves you with a clearer sense of what had to change. In science, those are often the most instructive moments. Not when a theory glides smoothly over experience, but when experience corners the theory and refuses to let it pass without a confession. There is also a deeper lesson about light itself here. Light is not just something that travels through the universe, it reveals the universe to itself. By refusing to be caught, by refusing to possess a normal rest frame, by forcing observers to reorganize their measurements of time and space, light acts like a diagnostic tool for reality. It shows where classical intuition fails. It identifies the invariant structure hidden underneath appearances. It exposes the fact that the world is built around a causal boundary and not around the loose additive habits of everyday speed. Later developments in physics only strengthened this lesson. When quantum theory entered and the electromagnetic field acquired its quantum description, the impossibility of chasing light in the classical sense did not vanish. It became woven into an even richer framework. Photons are not tiny billiard balls waiting to be overtaken by a determined pilot. They are massless excitations of a field, and their behavior is inseparable from the relativistic structure of spacetime. The more deeply physics described light, the less sense the old catching-up picture made. That is where the later work of people like Feynman becomes so important, though we are not quite ready to stay there yet. Feynman helped build the modern language in which light and matter interact consistently at the quantum level. In that language, the special status of light is not an awkward leftover from Einstein. It is part of the basic architecture. The electromagnetic field, the behavior of photons, the local structure of interactions, and the causal order enforced by relativity all fit together. Chasing a beam no longer looks like a near miss in engineering. It looks like a category mistake. And still, it is worth lingering on the human side of the question. There is something wonderful about the fact that a simple act of imagination could reveal so much. No particle accelerator was needed for the first step. No giant telescope, just a mind willing to ask what would happen if I moved with the light. That does not mean experiments were unimportant. They were crucial, but thought experiments of this kind can reach into the heart of a theory and show where its assumptions no longer fit. Einstein had that gift. He could take a quiet mental picture and let it detonate inside classical physics. By now the outline should be clear. If you try to chase a beam of light using classical ideas, you expect to be able to match its speed and see a frozen wave. But the laws of electromagnetism do not allow such a frozen wave. Therefore, the classical assumptions about time, space, and velocity must fail. Relativity replaces them with a structure in which all inertial observers measure the same light speed, no observer can possess a rest frame moving with light, and massive objects can approach, but never reach the invariant boundary. The question of chasing light is not answered by better engines. It is answered by a new conception of motion, which leads directly to the next issue. If the impossibility of catching light is tied to the difference between massive and massless motion, then we need to look much more closely at what mass is doing in this story. Why does having mass prevent an object from ever drawing level with the beam? Why does the addition of more energy keep changing the motion without ever completing the chase? And why does the boundary become more stubborn the nearer you come to it, as if the universe were not merely limiting speed, but distinguishing between two fundamentally different kinds of existence in motion? The reason the chase never ends is not that matter is slow in the ordinary sense. It is not that atoms are clumsy, or that spacecraft are badly designed, or that the universe is setting a difficult challenge just to be theatrical. The problem is deeper than that. Mass changes the kind of motion an object is allowed to have. Once something has mass, it belongs to a category that can move through space at many different speeds, but can never move through space in the same way that light does. That difference is not a matter of determination. It is built into the structure of space-time itself. This is one of the places where everyday intuition becomes actively misleading, because ordinary experience trains us to think that more energy simply means more speed. Push a cart and it rolls. Push it harder and it rolls faster. Throw a stone gently and it drifts. Throw it harder and it goes farther and faster. Accelerate a car and the speed climbs with the effort. Nothing in normal life prepares us for a point where the very meaning of adding energy begins to change. We are used to motion behaving like a scale, with no sharp distinction at the top. Slow, medium, fast, faster still, on and on. But relativity says that is not how the deeper structure works. For an object with mass, every increase in speed changes the situation in two ways at once. The object is moving faster through space, yes, but it is also entering a regime where the relation between energy, momentum, time, and distance becomes less and less classical. The old expectation that each new push should produce the same sort of speed gain starts to fail. At low speed, the difference is tiny, so tiny that everyday life gives us no warning. A ball thrown across a garden behaves almost exactly as common sense predicts. A plane crossing an ocean does too. Even a planet circling a star is often close enough to the classical picture for the older intuition to survive with only small corrections. But as the speed rises closer to the universal limit, the hidden structure becomes impossible to ignore. The mistake many people make is to imagine the speed of light as though it were simply an especially high number waiting at the end of a long road. In that picture, matter starts far back on the road and just needs enough energy to keep climbing until it reaches the final milestone. That sounds reasonable because it treats motion as one continuous ladder. Yet the ladder metaphor fails. The speed of light is not the last rung on the same staircase. It is a boundary between different kinds of motion. Massive objects live on one side of that boundary. Massless ones live on the boundary itself. No amount of pushing turns one category into the other. To feel this more clearly, it helps to stop thinking of motion as something that happens only in space. That is how human intuition usually frames it. You are here, later you're there. The faster you go, the more quickly you cover the distance. But relativity tells us that the deeper description is motion through space-time, not just through space. Every object traces out a path through the combined structure of space and time. Once you look at things that way, the difference between massless and massive motion is not just a matter of rate, it is a matter of what kind of path is available. A massive object always has its own passage of time. A clock carried with it ticks. Processes inside it unfold. If it is a person, their heart beats, their thoughts proceed, their body ages. If it is a particle with mass, it still has a meaningful progression along its path. Light is different. Light does not have a normal rest frame in which it sits still and lets time pass around it in the ordinary way. It does not belong to the same family of trajectories. That is why trying to push matter up until it behaves like light is not like pushing a bicycle until it behaves like a faster bicycle. It is like trying to push a fish until it becomes a river. The categories do not merge just because the effort increases. This is also why mass matters so much. In ordinary speech, mass sounds like a simple measure of how much stuff something contains, or how hard it is to shove across the floor. Those are rough everyday meanings, and they are useful within limits. But in modern physics, mass is tied to something more fundamental. It is part of what determines how an object exists in space-time and how it responds to forces and fields. Once an object has non-zero rest mass, it can be at rest in some frame. It can move slower than light, and it must remain below that limit. The structure of the theory does not offer a lawful route for that object to accelerate into the light-like category. You can see the practical consequence of this in particle accelerators. These machines push charged particles to astonishing speeds, far beyond anything familiar in ordinary life. As the particles gain energy, they do move faster, but after a point most of the added energy is no longer showing up as the simple kind of speed increase that common sense expects. The particles get closer and closer to the speed of light, but never arrive. The gap shrinks, yet the limit remains untouched. This is not because engineers gave up too early or because nature is hiding a final little reserve of speed behind a locked door. It is because the structure of relativistic motion makes the last part of the chase fundamentally unreachable for matter. At this point, some people wonder whether the problem is just one of scale. Could not an absurdly large amount of energy bridge the final difference? Could not some unimaginably advanced civilization build a machine powerful enough to do what we cannot? But this way of thinking still treats the situation as though there were a finite obstacle to overcome. There is not. The closer a massive object gets to the limit, the more severe the cost of further progress becomes. There is no final last step waiting to be taken. There is only an endless approach. The universe does not offer a point at which matter suddenly crosses over and joins light. It offers a boundary that matter can approach without end. This is one reason the phrase cannot reach the speed of light is stronger than it first sounds. It does not mean difficult to reach. It does not mean very unlikely. It does not mean unreachable with current technology, but perhaps achievable later. It means that within the framework of relativity, the distinction between massive and massless motion is exact. A massive object can be arbitrarily close to light speed in principle, but it cannot be there. The difference may become tiny beyond ordinary comprehension, but it never disappears. There is an important conceptual shift hidden in this. In classical mechanics, energy and speed are closely tied in the straightforward way our daily experience suggests. In relativity, energy is still tied to motion, but the geometry of spacetime changes the relationship. Added energy can continue to pour into the motion of a particle without producing proportionate increases in speed. Instead, the object carries more momentum and more energy, while its speed creeps ever more reluctantly toward the boundary. If you insist on using purely classical language for this, the situation sounds absurd. It feels as if the object is swallowing energy without properly showing it in its speed. But the absurdity comes from using the wrong conceptual frame. The energy is not disappearing. The old expectation about speed gain is what fails. There is a deeper reason for this, and it takes us back to causality. The invariant speed is not just a statement about how fast light goes, it is part of the structure that keeps causes and effects in consistent order. If massive particles carrying information, matter and interactions could simply be pushed past that boundary, the causal structure of space-time would come apart. Different observers could disagree in dangerous ways about which event produced which. Signals could, in some frames, appear to arrive before they were sent. The orderly web of physical explanation would start to fray. So the fact that mass can never quite catch up is not a random inconvenience. It is one of the mechanisms by which the universe preserves a stable causal framework. This is also why the difference between mass and no mass is not cosmetic. A massless entity such as a photon does not need to be accelerated up to the limiting speed. It exists on that boundary from the beginning. Its nature already fits the space-time structure that defines the maximum speed. A massive object, by contrast, belongs to the interior of that structure. It can move in many ways, but all of them lie strictly below the boundary. To move like light would require it not merely to go faster, but to cease being the kind of thing it is. That wording may sound dramatic, but it is the cleanest way to say it. The problem is not that matter needs more effort. The problem is that matter and light are not separated by a practical difference only. They are separated by a structural distinction. The speed limit marks the edge of one category of existence in motion and the location of another. One useful way to think about it is through clocks. A massive object can carry a clock. Even if it is moving very fast, there is a meaningful sense in which time passes along its own path. Relativity tells us that this passage can differ from what another observer measures, but it is still real for the object. Light does not fit that picture. There is no ordinary clock riding alongside a photon in a rest frame of the photon, because there is no such rest frame. This is not a technical gap that future physics is expected to fill with a better travel brochure for photons. It is a consequence of how massless motion sits at the causal boundary of space-time. Once you understand that, the impossibility of catching up ceases to be mysterious in the old mechanical sense. It becomes a reflection of what sort of path through reality matter is permitted to take. This also sheds light on why acceleration cannot solve the problem by brute force. We often imagine acceleration as a universal tool. If you're not going fast enough, accelerate longer. If you still are not fast enough, build a stronger engine. But acceleration only changes velocity within the range allowed by the geometry of space-time and the nature of the object being accelerated. It cannot change a massive object into a massless one merely by adding more energy. There is no hidden threshold at which the laws suddenly say, All right then, you have tried hard enough. You may now behave like light. The laws are stricter than that. What makes this even more interesting is that the limit does not merely constrain giant spaceships in science fiction scenarios. It is already present in the behaviour of tiny particles, electrons in accelerators, muons in storage rings, cosmic rays crossing the galaxy. All of them reveal the same structure. Massive particles can be driven to speeds extremely close to light speed, and when they are, the relativistic effects become measurable and undeniable. Time dilation is observed, energies rise enormously. The particle dynamics follow the relativistic rules, yet the boundary remains uncrossed. This repeated experimental fact is one of the reasons the limit is not a philosophical preference. It is part of the tested fabric of the theory. There is also a subtle lesson here about the word catch-up. In daily speech, catching up means reducing a gap until the gap vanishes. But the gap between matter and light is not like the gap between two runners on a track. It is more like the difference between approaching a horizon and arriving at a destination. The closer you get, the more the structure of your description matters. In relativity, the closer you push a massive object toward the invariant speed, the more distorted the classical language of pursuit becomes. The chase is not failing because the object is almost there, but not quite lucky enough. The chase was misconceived from the start as a race within one category, when it is really an approach toward a boundary between categories. This helps explain why the speed limit is so often misunderstood in popular accounts. It is tempting to say that matter becomes infinitely hard to accelerate to light speed, and while that points in the right direction, it can still sound like a practical engineering problem taken to an extreme. The more accurate picture is that the laws of space-time and energy do not permit a massive object to have a light-like trajectory. The impossibility is not about strained machinery, it is about the allowed structure of motion. A better engine does not solve that any more than better hiking boots solve the problem of walking north of the North Pole. At the same time, it is important not to make the story sound more mystical than it is. This is not a magical prohibition. Physics is not saying that matter approaches the limit and then encounters some invisible hand that says stop. The behaviour arises naturally from the way relativistic motion is defined. Once you formulate space and time in the correct way, once you require consistent causality, and once you distinguish the allowable paths of massive and massless entities, the result follows. The wall is not added from outside, it is internal to the system. Now, this distinction between mass and light becomes even richer when quantum theory enters. In quantum field theory, particles are not treated as tiny hard pellets with intrinsic little motors. They are excitations of fields. Mass too takes on a deeper meaning in that framework. Some fields correspond to massless particles, others correspond to massive ones. Their permitted motions and interactions reflect those differences from the start. This does not erase the relativistic story, it deepens it. Instead of asking why one little object cannot catch another little object, we ask how different field excitations propagate through space-time and why some sit on the causal boundary while others remain within it. That is one place where later physics, including the work associated with Feynman, becomes essential. Once you describe nature in terms of fields and quantum interactions, the impossibility of matter catching light is no longer just a consequence of a few abstract postulates in relativity. It becomes woven into the local structure of interactions themselves. Photons are massless, and therefore travel at the invariant speed. Electrons have mass and therefore do not. Their interactions must respect the causal order encoded by relativistic field theory. What looked from a distance like a strange limitation on speed turns out to be part of the load-bearing design of the quantum world. But before settling there, it is worth staying with the human side of the question a little longer. It is not obvious, when first encountered, that mass should have anything to do with the final speed limit of the universe. In ordinary life, mass feels like a resistance to starting and stopping, not a passport category determining your relation to causality itself. Yet that is exactly what modern physics reveals. Mass is not just how stubborn an object feels when you try to move the furniture. It is part of what determines which region of spacetime behaviour the object belongs to. And this is one of the reasons relativity remains so effective at correcting intuition. It does not simply tell us a surprising fact. It takes several everyday ideas that seemed unrelated and shows that they were connected all along. Motion, time, energy, mass, and causality are not separate topics awkwardly sharing a textbook. They are aspects of one structure. The reason mass can never quite catch up is therefore not one isolated trick of the theory. It is the combined expression of that whole structure operating consistently. Once that becomes clear, another question begins to press forward. If massless things, such as photons, naturally occupy the boundary that massive things can never reach, then what exactly are photons doing? What is the real nature of light in this deeper picture? Why does empty space allow these massless excitations to move in the way it does? And how did later physicists, especially Feynman, uncover the hidden rules governing those interactions so successfully that the speed limit stopped looking like an abstract decree and started looking like a direct consequence of how reality is assembled from fields, particles, and the vacuum itself? So now we arrive at the part of the story where the old image of empty space finally has to be abandoned. Up to this point we have been talking about light speed as a limit built into space-time, about the difference between massive and massless motion, and about why matter can approach the boundary without ever reaching it. All of that already tells us something profound, but it still leaves one quiet assumption standing in the background, and it is an assumption most people carry without noticing. We tend to imagine that once the stars and planets and particles have been taken away, what remains is simply nothing. A blank stage, a passive emptiness, a clean absence through which light travels and matter moves. That picture is too simple. Modern physics does not treat empty space as mere absence. It treats it as a place where fields exist, where interactions are possible, and where the rules of the universe remain fully active even when no visible object seems to be present. That shift matters enormously, because once you stop imagining space as dead emptiness, the speed of light begins to look less like an arbitrary speed limit and more like part of the operating rules of a structured vacuum. And this is where Richard Feynman becomes central, not because he invented relativity and not because he discovered the speed limit itself, but because he helped reveal how light and matter actually behave inside this deeper framework. Feynman entered physics at a time when the old classical picture had already been broken open. Einstein had transformed our understanding of space and time. Quantum theory had shown that atoms, radiation, and matter do not obey the calm mechanical logic of older physics. Yet there was still a major problem waiting to be solved. Physicists had pieces of the truth, but the pieces were difficult to fit together cleanly. They needed a theory of light and matter that respected both relativity and quantum principles at once. They needed a way to describe electrons, photons, electromagnetic interactions, and the vacuum itself without letting the mathematics collapse into nonsense. That sounds technical, and it is technical, but the basic issue can be stated very simply. How does one charged particle affect another? Not in the vague everyday sense, not by saying it exerts a force and leaving it at that. What is really happening in a world where light is quantum, matter is quantum, and the speed of a light defines the causal order of events? How do those interactions take place in a way that is both local and consistent? The older language of forces had already done useful work. It let people calculate electric attraction, magnetic behaviour, radiation, and a great many ordinary things. But as physics pushed deeper, it became clear that a more fundamental picture was needed. The world was not best described as tiny billiard balls reaching across space with invisible strings attached. It was better described in terms of fields, with particles appearing as quanta or excitations of those fields. The electromagnetic field was not just a mathematical convenience. It was real in the sense that it carried energy, momentum, and disturbances. Light itself was tied to this field. Matter too had to be understood in a field-based way. This is where the vacuum begins to change character. If fields fill space, then empty space is not the absence of all physical content. It is the state in which those fields exist even when no obvious particles are present. That does not mean empty space is stuffed with hidden furniture waiting to trip over you in the dark. It means that what counts as nothing in modern physics is already more structured than the old picture allowed. A vacuum is not a hole in reality. It is one of the possible states of reality. Feynman helped make this intelligible in a way that was both powerful and practical. One of his great gifts was not merely that he could solve hard problems, but that he could find a language for them that exposed the process underneath. He developed ways of organizing quantum interactions that let physicists calculate what would happen when light and matter met. These methods made it possible to describe an electron emitting or absorbing a photon, two electrons influencing one another through the electromagnetic field, and all the subtle corrections that arise because the quantum vacuum is not as inactive as classical common sense once supposed. Before this development, the situation was deeply frustrating. The existing quantum descriptions of the electromagnetic field tended to produce infinities in places where physical answers should have been finite. It looked at times as though the theory might simply be sick at its core. That would have been disastrous because the theory in question was supposed to describe some of the most basic interactions in nature. Yet the experiments were also insisting that the general framework was onto something real. So the task was not to throw the whole thing away, but to understand what the theory was trying to say and how to extract meaningful predictions from it. Feynman was one of the people who helped turn this crisis into one of the greatest successes in physics. The resulting theory, quantum electrodynamics, became the most precise physical theory ever tested. That phrase gets repeated often, but it matters here for a specific reason. It means that the hidden rules of empty space, the interaction of light and charged matter, were not just guessed at in a poetic mood and then admired from a distance. They were turned into a framework that could predict measurable quantities with extraordinary accuracy. Tiny shifts in energy levels, subtle corrections to magnetic behavior, scattering outcomes in particle experiments, all of these could be computed and compared with experiment, and they matched. That success tells us something very important about the vacuum. It tells us that empty space is not featureless. If it were, the interaction of electrons and photons would be far simpler than it actually is. Instead, the vacuum of quantum field theory permits fluctuations, intermediate processes, and a whole careful accounting of what can happen during an interaction, so long as the final observable outcome respects the rules. Empty space is therefore not a passive stage on which matter performs. It is part of the performance. Now, it is easy to talk about this in a way that makes it sound either mystical or cartoonish, and both temptations should be resisted. On the mystical side, people sometimes hear that the vacuum is active, and immediately imagine that nothingness is secretly magical, bubbling with spontaneous creation in a way that dissolves all discipline. It does not. On the cartoonish side, people hear about virtual particles and start picturing tiny objects constantly popping in and out, like over-enthusiastic stage actors who have not read the script. That picture can be suggestive in the loosest sense, but it is also misleading if taken too literally. The deeper truth is more sober. The quantum vacuum allows contributions to interactions that go beyond a single simple path. These contributions must be included when calculating real outcomes. They reflect the structure of the theory, not a childlike fireworks display of objects appearing from nowhere in the everyday sense. Feynman was especially brilliant at finding ways to represent these processes without drowning in impossible complexity. His diagrams became famous because they compressed difficult interactions into clear visual stories. An electron goes here, a photon is exchanged there. Another interaction occurs later. To a non-physicist, these diagrams can look deceptively simple, as though physics had finally decided to become polite and draw a map. But the diagrams are not just pictures. They are organized pieces of a calculation. They show the possible ways an interaction can unfold in spacetime, and they encode the rules for contributing to the total probability of an outcome. This is where the hidden rules of empty space begin to feel real in a new way. Suppose two electrons repel each other. In older language, you might say they just feel an electric force. In the field-based quantum picture, the interaction is described through the electromagnetic field, with photons playing the role of carriers of that interaction. Not necessarily visible light, not little flashes you could watch with a magnifying glass, but quantum excitations associated with the field. The electrons do not need to touch in the classical sense. They interact locally with the field, and the field carries the influence according to the rules permitted by relativity and quantum mechanics. That local structure matters enormously. It means the universe is not operating by vague, long-distance sympathy. One object does not simply decide to affect another by sheer opinion. Interactions are built out of local events connected by fields. This is one reason the speed of light remains so fundamental even in the quantum picture. The field does not send influences however it pleases. The causal structure set by relativity still governs what is allowed. Feynman work did not weaken the speed limit. It helped show how quantum interactions could respect it while still producing the rich behavior we observe. This point is sometimes missed because people assume quantum theory must be a rebellion against all order. They hear uncertainty and probability and conclude that physics has given up on structure. It has not. Quantum theory changes the kind of structure we use, but it does not dissolve the rules. In fact, quantum electrodynamics is one of the most disciplined frameworks ever constructed. The interactions are constrained, the vacuum is structured, causality remains protected. The speed of light still marks the boundary for how influence propagates through spacetime. Feynman's contribution also changed how physicists thought about the path from one event to another. In ordinary life, if something moves from one place to another, we imagine a single path, perhaps the obvious one. Feynman introduced a way of thinking in which the full quantum behavior arises from considering all the possible histories consistent with the situation, with each contributing to the final result. This sounds alarming at first, as though the universe cannot make up its mind and so tries everything. But the real lesson is more disciplined than that. Nature at the quantum level is not described by one simple classical route. To compute what actually happens, one must account for all allowed contributions and how they combine. This way of thinking becomes especially powerful when applied to light. Light does not travel as if it were a tiny classical pellet choosing one neat path through a dead vacuum. Its behavior reflects the quantum structure of the electromagnetic field. The vacuum through which it moves is governed by field laws. Its interactions with matter are not simple collisions between miniature hard beads. They are local quantum processes that must be summed consistently. Once you begin to see that, the speed of light stops looking like an isolated oddity and starts looking like one of the organizing principles of the entire framework. Another crucial development concerns the self-interaction corrections that appear when charged particles and the electromagnetic field influence one another. An electron is not just a bare little object sailing untouched through space. In the theory, it is surrounded by the effects of its interaction with the field. The vacuum and the field contribute subtle corrections to its behavior. Early calculations of these effects often produced infinities, which at first looked like a sign that the theory had gone off the rails. The breakthrough came when physicists, including Fineman, learned how to handle these divergences in a controlled way through the process known as renormalization. That word has frightened generations of students and inspired generations of smugness in people who have just learned it, but the important point for us is simpler. The theory could be reorganized so that the measurable quantities remained finite and meaningful. The infinities were not taken as signs that nature itself was nonsensical. They were signs that one had to describe the relation between the idealized parameters of the theory and the measured properties of real particles with greater care. Once that was done, the framework became stunningly successful. Why does that matter for our subject? Because it shows that empty space has hidden rules that are not optional decorations. Charged particles are not interacting against a perfectly blank background. The vacuum and the field structure affect what particles do. even when no obvious radiation is present. This means that the universe is much less like a sparse room with a few marbles rolling across the floor, and much more like a tightly regulated field environment in which every motion and interaction must be consistent with a deeper architecture. There is something almost severe about this picture. Empty space sounds gentle until physics inspects it. Then it turns out to be full of law. Not clutter, not ordinary matter, but law. The electromagnetic field is present as part of the fabric of the theory. The vacuum state is defined with respect to that field structure. Quantum processes include contributions that would never appear in a classical account, and throughout all of it, relativity still insists that causal influence respects the invariant speed. Feynman helped show how all these demands could coexist. He was also unusually good at preserving the physical intuition behind formal theory. Some physicists are extraordinary but speak as if they are testifying before a committee determined to outlaw clarity. Feynman could be playful, impatient, blunt, and brilliant, but he usually kept one eye on what the mathematics was trying to say about actual nature. This is part of why his work matters so much for this story. He did not just provide technical machinery. He helped people see that the vacuum is not emptiness in the old sense, that interactions are built from local quantum events, and that the behaviour of light and matter has to be understood inside that structured emptiness. This also brings us closer to the question of why light speed is the limit. In a purely classical mood, one might still imagine that the limit comes from nowhere in particular, as though the universe simply issued a decree. But once the field picture is taken seriously, the limit becomes more intimate. The electromagnetic field does not live outside space-time. It is part of the physical content of space-time. Photons, as massless excitations of that field, propagate according to the causal structure built into the geometry. Matter fields interact with the electromagnetic field locally, and cannot use those interactions to cheat causality. Empty space is therefore not something through which the rule passes. It is one of the places where the rule is implemented. That is a subtle but important shift. The speed of light is not merely the speed something happens to move through space. It is tied to how fields propagate in vacuum and how space-time organizes causal relations. Feynman's work helped make that picture calculable. He turned philosophical-sounding statements into equations that matched experiment. He made the hidden rules of empty space visible through prediction. And yet even here, one must be careful not to overclaim. Feynman did not explain everything. He did not uncover the final theory of all reality. He did not answer why the universe exists in exactly this form rather than another. What he did was something both more modest and more valuable. He helped reveal how the known interactions of light and charged matter work with astonishing precision, and in doing so he showed that the vacuum is an active participant in the structure of physical law. That is already one of the great achievements in science. It also means that when we speak about light moving at the ultimate speed, we should not imagine it as a lonely projectile darting through a silent void. We should imagine it as the behaviour of a massless field excitation in a vacuum that is structured by quantum law, relativistic causality, and local interaction rules that have been tested to extraordinary precision. That is a much richer statement. It is also much closer to what modern physics believes is really going on. By now, the old picture of nothingness should feel a little less secure. Empty space is not empty in the childish sense. It is lawful, structured, and physically meaningful. Feynman helped teach us how to think about that structure, how to calculate within it, and how to understand the interactions of light and matter as part of one coherent framework. Once that framework is in place, the next step becomes unavoidable. If photons are the massless quanta of the electromagnetic field, and if the vacuum itself plays such an important role in shaping interactions, then we need to look much more directly at the photons themselves, at what they are, at how they differ from our everyday idea of light, and at why their strange existence makes the universal speed limit feel less like a restriction and more like the natural behaviour of a very particular kind of thing. Once the vacuum stops looking like a blank emptiness and starts looking like a structured setting for fields and interactions, photons become much stranger than the everyday word light suggests. In ordinary language, light feels familiar. It is what fills a room when the curtains are opened. It is what reflects from faces, books, roads, clouds, and coffee mugs. It is what lets us recognize the world before we've had enough sleep to trust our own judgment. We speak of light as if it were a single simple thing, and at the level of daily life that is usually enough. But the deeper physics goes, the more it becomes clear that photons are not just little pieces of brightness, and not just miniature classical waves either. They belong to a category of existence that forced 20th century physics to reinvent its description of reality. The first surprise is that a photon is not best understood as a tiny glowing bead shooting through space like a microscopic bullet. That image is common because it is easy to picture. It makes light feel manageable, but the image fails in important ways. At the same time, the old image of light as only a spread out classical wave also fails. If you cling too tightly to the wave picture, you cannot explain why light sometimes arrives in discrete detectable amounts, why atoms emit and absorb radiation in quantized ways, or why many of the most important experiments in modern physics behave as they do. The photon emerges precisely because neither of the simpler pictures is enough on its own. This is where people often become tempted to ask which one light really is. Is it a wave or a particle? The honest answer is that the question is too crude. The photon is part of the quantum electromagnetic field. It behaves in ways that carry features we once associated separately with waves and particles, but it is not fully captured by either old category in its naive form. That is not physics being evasive. It is physics telling us that the classical language we inherited from everyday life was built for apples, ripples, thrown stones, shadows, and the usual household disasters, not for quantum fields. Still, the particle language remains useful if it is handled carefully. A photon is the quantum of the electromagnetic field, the smallest discrete excitation in the sense relevant to that field. When light interacts with matter, it often does so in these discrete packages. An atom does not usually sip from a continuous mist of electromagnetic energy in any arbitrary amount it likes. It absorbs or emits in specific quantized ways. Detectors click discretely. Photoelectric processes occur in countable events. These facts were among the clues that light could not remain merely a smooth classical wave. Yet the wave features do not disappear just because discreteness enters the story. Light still interferes, it still diffracts. It still produces patterns that make no sense if you imagine individual photons as tiny pebbles, simply taking one classical path each and ignoring every other possibility. This is one of the reasons photons are so important for understanding the quantum world. They force us to confront the fact that nature does not organize itself according to the categories that feel most intuitive to us. The photon is not a compromise between wave and particle. It is a deeper object from which the older descriptions emerge only in limited ways, and this matters directly for the speed limit. The more clearly we understand what a photon is, the less mysterious it becomes that it moves at the invariant speed. A photon is not a tiny material lump being hurled through the vacuum with exceptional enthusiasm. It is a massless excitation of the electromagnetic field. In the structure of relativity and field theory, massless excitations propagate at the universal speed that defines the causal boundary of spacetime. So the photon does not have to be accelerated to that speed. It does not struggle to get there. It is not racing towards some finish line. Its very nature places it on that boundary from the outset. This is why the phrase "the secret life of photons" is useful. The secret is not that photons are doing something dramatic behind our backs. The secret is that our first picture of them is almost always too small. We think of light as illumination. Physics finds a massless quantum field excitation. We think of a beam as a stream of tiny objects. Physics finds amplitudes, interference, probabilities, and local interactions with matter. We think of empty space as nothing. Physics finds a vacuum state structured by field laws. The deeper picture does not replace the familiar one in everyday life, but it does show how much was hiding underneath it. One of the most important hidden facts is that photons are the carriers of electromagnetic interaction in quantum electrodynamics. This does not mean every ordinary push and pull in daily life should be visualized in cartoon form as visible little sparks bouncing around between objects. That would not be helpful, and would probably make opening a drawer feel more intimidating than it needs to. But it does mean that the electromagnetic field is not merely a distant abstraction. It is part of the machinery by which charged matter influences charged matter, and photons are central to that machinery. When two charged particles interact, the modern description does not treat them as simply reaching across space with a force like invisible fingertips. Instead, the interaction is described through the field, with photon exchange appearing in the quantum account of the process. Some of these photons are not real observable photons in the same sense as the light arriving from a lamp or star. They are part of the internal bookkeeping of the interaction, constrained by the rules of the theory. This can sound annoyingly abstract at first, but the key point is straightforward. Electromagnetic interaction is mediated, local, and structured. The photon is not just a messenger of brightness. It is a participant in the way the universe organizes one of its fundamental interactions. That already makes photons special, but there is more. A photon has no rest mass, and that has consequences that go far beyond speed alone. Because it has no rest mass, there is no inertial frame in which a photon is at rest. You cannot ride alongside one and treat it as an ordinary stationary object. You cannot assign it a normal rest state in the way you can for a massive particle. This is why all the old imagery about catching up to light fails so badly. A photon is not the sort of thing that can be brought to rest by changing your viewpoint. It belongs to the boundary structure of spacetime itself. Another way to say this is that photons do not inhabit the world the way matter does. Matter with mass can linger, rest, accelerate from slowness to speed, and be described in a frame where it is not moving spatially. Photons do not have that option. Their existence is tied to propagation at the invariant speed. This does not make them less real than matter. It makes them differently real. That distinction is easy to miss because ordinary language tends to flatten everything into the same category of object. Physics keeps discovering that nature is less democratic than language. It sorts things into classes that behave according to different deep rules. Photons are also peculiar in the way they carry energy and momentum without carrying rest mass. That sounds almost contradictory from a classical viewpoint. In everyday life, we associate impact, transfer, and momentum with material bodies. A moving ball can strike something. A gust of wind can push against a sail. It feels natural to connect the ability to transfer momentum with having matter in the ordinary sense. Yet light can push as well. Radiation can exert pressure. Photons can transfer momentum in interactions. The sun does not merely illuminate the solar system. Its light carries energy outward through space in a physically effective way. Again, the lesson is that the old categories were too narrow. Rest mass is not required for all of the physical roles. Common sense once assigned only to material objects. There is also the issue of identity. Classical objects tend to encourage a simple story. One object goes from here to there along some definite path. You may not know the path exactly, but the object is imagined to have one all the same. Photons do not fit comfortably into that classical narrative. In quantum experiments, they display interference behavior that forces us to abandon the idea that each photon always travels one neat, little predetermined route in the ordinary sense. Feynman was especially powerful on this point. His way of describing light often emphasized that the correct calculation involves considering all the possible paths that contribute, not merely the single path classical intuition would like to privilege. That does not mean a photon is literally a tiny conscious explorer trying every road at once out of indecision. It means that the quantum description of propagation is built from amplitudes associated with different possible histories, and the observable result depends on how those amplitudes combine. The phrase all paths is therefore not an invitation to fantasy. It is a disciplined statement about the structure of the theory. Still, the emotional impact of it is hard to overstate. The photon does not move like a classical pellet in a passive void. Its behaviour reflects the full quantum structure of field propagation. This is one reason photons have always been such good teachers of modern physics. They reveal the failure of too much certainty in the classical picture. They refuse to sit still for our preferred metaphors. Treat them only as waves and they revolt. Treat them only as particles and they revolt again. Try to assign them a normal rest frame and they refuse. Imagine them as little marbles flying through empty nothingness, and field theory steps in to tell you that the vacuum itself has more structure than that. The photon is, in a sense, the universe's constant reminder that naive realism has limits. And yet, photons are not exotic in the sense of being rare or remote. They are everywhere. Nearly everything you know directly about the cosmos has reached you through photons. The stars announce themselves through photons. Galaxies reveal their motions, temperatures, and compositions through photons. Your surroundings become visible through photons scattered into your eyes. Even much of physics history was written by following what light does. In that respect, the photon is both the most ordinary and the most philosophically disruptive of entities. It is familiar enough to seem boring and strange enough to overthrow an entire conception of reality. There is a particularly important connection here to information. In modern physics, the speed of light is often described as the maximum speed for information transfer or causal influence. Photons are central to that story because they are among the most direct carriers of signals through empty space. Radio communication, visible light, X-rays, gamma rays, all of these belong to the electromagnetic family. Different frequencies, different contexts, same underlying field. The photon is therefore not just a quantum curiosity, it is one of the main ways the universe communicates across distance. And because photons are massless, that communication occurs at the invariant speed. This is another reason the speed limit is less arbitrary once photons are understood properly. It is not as though the universe first decided on a random maximum and then later assigned photons to obey it. Rather, the field structure of the vacuum and the geometry of spacetime already support a class of massless excitations whose propagation defines the causal boundary. Photons are the most familiar members of that class. They do not illustrate a rule from outside, they embody it. Still, there is room here for caution. It is easy to slip into the idea that photons are tiny courier objects carrying messages like microscopic postal workers. That metaphor is charming for about 6 seconds, and then becomes misleading. A photon is not a miniature envelope with energy stamped on the front. The electromagnetic field and its quantum excitations are described by a theory in which locality, amplitudes, and interactions matter more than our favourite household analogies. The value of the photon concept lies not in how cute a picture we can attach to it, but in how precisely it describes the quantized behaviour of electromagnetic phenomena. One of the most beautiful demonstrations of the photon's strange nature is the photoelectric effect. Light shining on a material can eject electrons, but the effect depends on the frequency of the light, not just its overall intensity in the smooth classical wave sense. That result made it impossible to keep pretending that light was only a continuous wave delivering energy in any amount whatsoever. The interaction came in discrete quanta. This was one of the early pieces of evidence that something like the photon had to be real. And from there the conceptual revolution only deepened. Spectra, atomic transitions, scattering experiments, all began to reveal a world in which light was quantized and matter responded accordingly. Then came the even more unsettling realization that single photons can build interference patterns over many repeated events, as if the wave aspect were somehow inseparable from the discrete detection events. This is precisely the sort of thing that makes the quantum world feel less like an extension of common sense and more like a careful correction of it. The photon does not alternate between being a wave on Tuesdays and a particle on weekends. It is described by a quantum framework in which both kinds of classical behaviour emerge in different aspects of the phenomenon. The discomfort comes from trying to fit the whole story into one outdated box. Photons are also deeply tied to symmetry. Without wandering too far into a thicket of formalism, it is worth noticing that the electromagnetic field is not just any field among others. Its structure reflects deep principles that shape the theory. The photon arises not as a decorative add-on, but as part of a mathematically constrained framework that preserves consistency. This is another reason Feynman's work mattered so much. He did not merely help compute isolated effects. He worked within and helped clarify a theory whose success depended on respecting these deeper structural demands. The photon, the field, the vacuum, and the speed limit all belong to one architecture, and the more successful that architecture became experimentally, the less room there was for loose intuitive alternatives. You could not say photons were just convenient fictions, because detectors kept behaving as though the quantized picture was right. You could not say the vacuum was just nothing, because the theory predictions depended on vacuum structure and corrections that experiments confirmed. You could not say the speed of light was just an accidental property of visible radiation, because the relativistic and quantum framework kept revealing it as a causal boundary built into the laws themselves. The secret life of photons kept turning out not to be a metaphor, but a measurable fact. It is worth pausing for a moment on how odd that is. The same thing that lights your room is also a massless quantum of a field, a mediator of electromagnetic interaction, a participant in interference, a carrier of momentum, a revealer of quantum discreetness, and a visible marker of the causal structure of space-time. That is an extraordinary amount of responsibility for something most of us mainly notice when we cannot find the light switch. Yet that is often how physics works. The familiar turns out to be profound once examined closely enough. By now the pattern should be visible. The photon is not fast because it is clever, tiny, or especially determined. It is fast because massless excitations of the electromagnetic field propagate at the invariant speed allowed by the structure of space-time. The photon is not mysterious because science lacks detail. It is mysterious because the details themselves overturn classical intuition. The photon is not just a messenger from distant stars. It is one of the reasons we understand what a star, a field, and a causal structure are in the first place. And once that much is clear, the next step opens almost by itself. If photons are excitations of the electromagnetic field, and if their behaviour makes sense only inside a universe built from interacting fields rather than isolated little objects, then we need to widen the view. We need to stop talking about light and matter as separate actors meeting occasionally, and start talking about fields, forces, and the deeper machinery from which both emerge as part of one connected physical reality. Once you widen the view from photons alone to the deeper framework they belong to, the whole picture of reality starts to shift. The old instinct is to imagine a universe built from objects first, with forces added afterward like invisible ropes between them. A planet pulls on a moon, a magnet tugs at a nail, an electron pushes another electron away. This language is not useless. It works well enough in many ordinary contexts, and for a long time it helped physicists describe the world with impressive success. But the deeper physics goes, the more the older picture begins to look like a rough shorthand rather than the final story. The universe is not best understood as a collection of separate little things floating in an empty void and reaching out across distance. It is better understood as a structured network of fields, with what we call particles appearing as excitations of those fields, and what we call forces emerging from the ways those fields interact. That is a major change in perspective, and it takes a little patience to feel why it matters. The word field is one of those scientific words that can sound either very ordinary or very intimidating depending on the day and how much sleep you got. In everyday speech, a field might be grass, soil, a fence, and perhaps one horse judging you from a distance. In physics, a field is something distributed through space and time, something that can have a value or a state at each point. That may sound abstract at first, but the idea is actually less mysterious than it seems. Temperature in a room can vary from place to place. That is a kind of field in the ordinary descriptive sense. Wind speed across a landscape can vary from point to point. That too can be treated as a field. In physics, electric and magnetic phenomena led naturally to the same kind of thinking. Instead of saying one charged object reaches across emptiness and somehow influences another directly, you say the charged object creates a condition in the surrounding space, and another object responds to that local condition. That step was one of the great conceptual advances in science, because it turned action at a distance into something more physical and more disciplined. A field lives in space. It changes over time. Disturbances in it can propagate. Energy can be carried by it. Once that picture is in place, the world becomes less magical and more structured. The price of the structure is that you can no longer imagine empty space as mere absence. If fields are real, then space is not just a blank gap between things. It is the setting in which the field exists, and through which its changes unfold. This is one reason the speed limit of light makes more sense once fields enter the story. If the universe were only separate objects with direct instantaneous influence, then asking why there is a maximum speed might feel arbitrary. But in a field-based world, the question becomes how fast disturbances in the fields can propagate while preserving the causal order of space-time. Suddenly, the existence of a limiting speed does not look like an odd restriction. It looks like part of the operating logic of the system. A field cannot send physical influence however it pleases. Its behaviour must respect the structure of space-time itself. Electromagnetism is the clearest example, because it was the first place where this deeper picture became unavoidable. Electric and magnetic effects turned out not to be separate little tricks of nature, but aspects of one unified field. Light itself turned out to be a wave in that field in the classical description, and later the photon emerged as the quantum of that same field. This is already enough to change the story completely. Light is not some extra messenger that happens to fly through the universe. It is the behaviour of one of the universe's most fundamental fields. When charged matter interacts, it does so through this field. When radiation travels, it is this field in motion. When photons are exchanged in quantum electrodynamics, they belong to this field structure. The electromagnetic field is not an afterthought. It is part of the machinery from which the observable world is built, and once you accept one field seriously, you're already halfway to accepting the whole field-based view of reality. Because the electromagnetic field is not alone. Modern physics describes matter itself through fields. The electron is associated with a field. So are quarks, so are other particles. The world is not made of little solid pellets moving through dead emptiness. It is made of interacting quantum fields whose excitations appear to us as particles when measured in the right way. This does not make particles unreal. It means particles are not the deepest starting point. They are the recognizable local manifestations of something more distributed and more fundamental. That sounds like a subtle distinction, but it has enormous consequences. In the older imagination, matter comes first and the vacuum is just the empty stage. In the modern view, fields come first and the vacuum is one possible state of those fields. Particles are then excitations above that state. Empty space is therefore not the total absence of physical content. It is the condition in which fields remain present without carrying the excitations we would identify as particles in the ordinary sense. That is why the vacuum can still have structure, why it can still influence interactions, and why the laws of physics remain fully active even when no obvious object is passing by to announce them. This is also why the word force becomes less central the deeper you go. In school-level descriptions, forces are introduced as the basic agents of change. Something pushes. Something pulls. Motion changes because a force acts. That is a useful entry point, but it is not how the most fundamental theories are usually organised. They are organized around fields, symmetries, interactions, and conservation laws. The language of force survives because it remains convenient at many scales, but underneath it the machinery is more local and more relational than the old picture suggested. Take two electrons repelling each other. In the old language, each electron simply exerts an electric force on the other. In the field-based quantum language, each electron is coupled to the electromagnetic field, and the interaction is described through that field. The influence is not a mystical tug across emptiness. It is a local interaction encoded in the structure of the theory. If you speak loosely, you can say the force is still there, and that is fine. But the deeper story is that the field is doing the work. This matters because it shows that reality is built from lawful processes rather than bare facts. The universe does not merely contain objects and a list of things they are allowed to do. It contains a machinery of interaction. Fields respond to fields, disturbances propagate, symmetries constrain behavior, conservation laws hold, causal order is preserved. Once you start seeing that, the world becomes less like a box of parts and more like a coherent dynamical system. Feynman's contribution fits naturally into this picture. His methods did not simply help physicists calculate a few isolated scattering events. They gave a practical language for tracing how quantum fields interact. A Fineman diagram is not a little comic strip of particles with secret feelings. It's a way of organizing the terms in a calculation so that the underlying interaction structure becomes manageable. An electron line, a photon line, a vertex where they meet. These are not decorations. They express the local rules by which the fields can affect one another. The simplicity of the drawing hides a remarkable amount of depth. It tells you that reality is not being described as disconnected things with forces stapled onto them. It is being described as a web of interactions generated by the couplings of fields. There is something very satisfying about that once it settles in. It means that the apparent solidity of the world is not primitive. It is constructed. The table feels solid not because its atoms are little hard marbles jammed together in the childish sense, but because the fields associated with matter and electromagnetism interact in ways that make compression, resistance, and stability possible. The colour of an object is not just a paint-like property sitting on its surface. It emerges from the interaction of light with the electronic structure of matter. Magnetism, chemistry, radiation, pressure, even much of what we call contact in daily life, all of it becomes part of one grand field-based account. And this is where the phrase machinery of reality earns its keep. Machinery does not mean gears, levers, and tiny engineers with excellent posture operating behind a curtain. It means an organised system of relations and rules that produces the phenomena we observe. Reality has machinery in that sense. Not visible machinery, but lawful structure. Fields provide the framework. Interactions provide the dynamics. Symmetry principles constrain what forms those interactions may take. The vacuum provides the stage state rather than an absence of law. Particles appear as local excitations. Measurements reveal discrete outcomes, and all of it has to fit within the relativistic demand that causal influence does not outrun the invariant speed. That last point is crucial, because it ties this whole field-based picture back to the speed limit that began our story. The machinery of reality is not allowed to work by instant action, across arbitrary distance. It must work locally. One field interacts here. The effect propagates outward according to the structure of space-time. Another field responds there. This locality is not merely a stylistic preference of theorists. It is part of what keeps the theory causal and coherent. If interactions could skip locality whenever convenient, then the whole framework would risk contradiction. The speed of light remains the boundary within which the machinery must operate. Now, locality does not mean simplicity in the everyday sense. Quantum theory makes sure of that. The possible contributions to an interaction can be rich, subtle, and difficult to picture classically. The vacuum can contribute corrections. Intermediate processes can matter. The full prediction may require summing many possibilities, not just tracing one neat little pathway. But none of that abolishes locality. It refines what locality means inside a quantum field theory. Physical interactions still arise from lawful local couplings of fields. They are not acts of telepathy between distant particles. This is one reason field theory is such a triumph of modern science. It managed to combine two demands that once looked almost impossible to reconcile. On one hand, quantum behavior is subtle, probabilistic, and far removed from classical imagery. On the other hand, relativity demands a stable causal structure and forbids unrestricted propagation of influence. A workable theory had to satisfy both. It had to let the world be quantum without becoming causally incoherent. The field-based framework, especially in the hands of the physicists who refined it through the 20th century, achieved exactly that. It provided a language in which particles are quantum, interactions are local, and the speed limit remains respected. There is also a deeper philosophical shift hiding in all of this. For centuries, people wanted the world to be made of things, little pieces of substance, little bits of matter, something you could imagine as fundamentally object-like. Fields complicate that desire because a field is not a thing in the old solid sense. It is extended. It exists across space. It can be calm or excited. It can support waves, quanta, and interactions. When you begin from fields instead of objects, the universe becomes less like a heap of building blocks and more like a patterned whole. This does not make it vague. Quite the opposite. It makes it more exact. But it does require giving up the comforting idea that the deepest layer of reality ought to resemble the most obvious furniture of ordinary life. And yet, in a different way, fields bring us closer to experience rather than farther away. Think about what we actually observe. We observe interactions, changes, relations, influences, propagation, and patterns. We do not directly observe tiny classical pellets with labels attached saying essence of matter. The field picture is strange, yes, but it captures the dynamical character of the world more honestly. It tells us that what is real is not only what sits in one place like a pebble. What is real is also what can extend, vary, propagate, and interact according to law. This is why the electromagnetic field was such a turning point. It taught physics that the world does not have to be understood in terms of matter alone. There can be physically real structures that are not ordinary objects and yet carry energy, momentum, and causal influence. Once that door opened, there was no going back to the most naive materialism of older mechanics. Reality had become richer. Particles still mattered, but they now lived inside a larger framework. The quantum version of this richness is even more striking. In quantum field theory, what looks like a particle in one context is a field excitation in another description. Creation and annihilation processes become natural rather than bizarre. Interactions no longer need to be described as eternally existing objects bumping into one another like stubborn marbles. Fields can exchange excitations. States can change. Numbers of particles need not remain fixed in all processes. The machinery of reality becomes more dynamic and more flexible than classical mechanics ever imagined, but it remains tightly constrained by symmetry, conservation, and causality. Symmetry deserves a moment here because it is one of the quiet architects of modern physics. By symmetry, physicists do not mean only visual balance or a pleasing geometric arrangement. They mean invariance under certain transformations, a deep statement that some aspect of the laws remains unchanged when you alter the description in a specified way. These symmetries are not cosmetic. They guide the form of the interactions themselves. They help determine what kinds of fields are possible, what couplings are allowed, and what conservation laws follow. The machinery of reality is therefore not just a pile of equations that happen to work. It has internal design principles. This is another reason the speed limit of light is not an isolated law floating above the rest. It belongs to the whole architecture. Space-time symmetry, field behavior, causal order, all of these support and require the invariant speed. The machinery is integrated. You do not get to remove the speed limit without damaging much else. You do not get to keep the local field structure, the relativistic symmetry, and the coherent causal order while casually allowing arbitrary faster-than-light influence. The pieces stand together. Even the ordinary distinction between matter and force begins to blur in this setting. Matter fields and interaction fields are not the same, but they are described within one common conceptual framework. Both are fields, both have quanta, both participate in the quantum structure of the vacuum. The old hierarchy in which matter was real and forces were secondary becomes harder to sustain. The deeper picture is that both belong to the same kind of ontology, if one allows a serious-sounding word to enter for a moment. They are both parts of what exists physically. And the success of this view is not merely philosophical elegance, it shows up in prediction, spectra, scattering amplitudes, magnetic moments, particle decays, radiation corrections, all the fussy little details that reality insists upon when you measure carefully, they come out right. That is why this whole field-based account must be taken seriously. It is not a poetic reinterpretation of known facts. It is the framework that actually lets us calculate the known facts with astonishing precision. Still, there is room for humility. The machinery of reality as we currently understand it is not necessarily the final machinery. Physics may yet discover deeper layers, new symmetries, or a broader framework from which our present theories emerge as approximations. But within the domains where our best theories have been tested, the field-based picture has earned extraordinary confidence. It has revealed that what seems like solid matter is inseparable from interaction. What seems like empty space is structured by vacuum states and fields. What seems like a simple force is often the visible effect of a much deeper local process. And what seems like a fixed speed for light turns out to be part of the logic by which the whole system remains coherent. That coherence matters. It means the universe can be complicated without being chaotic in the destructive sense. It can allow enormous variety while preserving internal discipline. Fields interact, but not arbitrarily. Forces emerge, but not without structure. Particles appear, but not outside the framework that defines them. The vacuum participates, but not as magic. Reality bends, shifts, and surprises, but it does so within laws strong enough to hold the whole arrangement together. And that idea of bending without breaking is exactly where the next part of the journey begins, because once you see the universe as a system of fields and interactions constrained by deep structure, another question becomes unavoidable. How much flexibility can those structures tolerate? How can space-time curve? How can fields fluctuate? How can quantum processes become wildly subtle? And yet the basic causal order and the light speed limit still survive without the universe tearing its own logic apart. Once you begin to see reality as a system of fields, interactions, and a space-time structure built around a fixed causal limit, a natural worry appears. If the universe is this complicated, if space-time can curve, if quantum fields can fluctuate, if particles can appear in interactions and disappear again, if the vacuum itself is structured rather than blank, then what exactly keeps the whole thing from becoming unstable? How much flexibility can nature allow before the system stops making sense? That question matters because physics, taken piece by piece, can start to sound like a catalogue of exceptions. Time is not absolute. Empty space is not empty. Light is both familiar and deeply strange. Matter is not fundamental in the old solid sense. Forces are fields. Observers disagree about durations and distances. Quantum processes do not behave like tiny mechanical models. At first, that can make the universe sound loose, slippery, almost improvised. But the truth is nearly the opposite. The universe bends in many ways, but it does not break. And the reason it does not break is that the flexibility is always controlled by deeper structure. A good example is space-time itself. Before Einstein, space and time looked rigid. Space was a passive stage. Time was a universal background flow. relativity changed that picture twice. First, special relativity showed that measurements of time and distance depend on motion, while preserving an invariant causal structure centered on the speed of light. Then general relativity went further and showed that space-time is not merely a neutral container even after that correction. It can curve. Matter and energy do not move through a fixed geometry that ignores them. They participate in shaping the geometry itself. That is an extraordinary level of flexibility. The very arena in which physics occurs is not fixed once and for all. It responds. And yet this does not mean all order is lost. Space-time does not curve however it pleases. Its curvature is constrained. The relation between geometry and matter is lawful. Light still follows the causal structure set by the space-time it inhabits. Massive objects still remain below the invariant speed in their local motion. Causality remains locally organized by the same limiting structure. In other words, general relativity did not overthrow the light speed limit. It embedded that limit inside a richer geometric setting. The universe bent the stage, but it did not tear up the rulebook. This is one of the most important habits of modern physics. When a theory becomes more subtle, it does not usually achieve that subtlety by throwing away all discipline. It achieves it by discovering a larger structure in which the older rule survives in a transformed but still essential way. The speed of light is a perfect example. In special relativity, it is the invariant speed linking space, and time and preserving causal order. In general relativity, where space-time can curve, local observers still find the same basic causal structure governing light and matter in their immediate region. The geometry may change from place to place, paths may bend, clocks may tick differently depending on gravity, but the local light cone structure remains central. The universe becomes more flexible without becoming arbitrary. That phrase, local structure, matters a great deal. Physics often avoids contradiction by insisting that laws retain a disciplined form locally, even when the global picture becomes more complicated. A straight line on a curved surface is a strange thing if you stare only at the whole surface, yet in a small enough neighbourhood the rules can still look clean and well behaved. Space-time in general relativity works in something like that way. Globally, the universe may contain curved regions, expanding regions, strong gravitational fields, or even black holes. Locally, however, the causal structure tied to the invariant speed still governs what can influence what. Light remains the boundary marker. Matter remains on the slower side of that boundary. The universe bends, but the causal framework does not dissolve. Gravity is not the only place where this pattern appears. Quantum field theory has its own kind of flexibility, and it too is tightly controlled. At first glance, quantum theory can sound like permission for almost anything. Particles do not follow neat classical paths. Outcomes are described probabilistically. Fields fluctuate. Vacuum effects contribute to measurable results. Internal processes and calculations can involve intermediate states that no classical imagination would ever invent on its own. But all of this happens inside a highly structured framework. The probability is not arbitrary. The interactions are constrained by symmetries. Conservation laws still hold. Locality is preserved in the way the theory is built. Relativity continues to limit the propagation of influence. Once again, the universe allows complication without surrendering coherence. This is one reason Feynman work mattered so much. He did not merely help physicists accept that the world is strange. Plenty of people were already aware of that. He helped show how the strangeness could be organized. His methods made it possible to calculate interactions in a theory where charged matter, photons, and the vacuum all contribute in subtle ways, while still preserving causality and consistency. That is what bending without breaking looks like in practice. The theory allows corrections, fluctuations, and multiple contributions to a process, but it does not allow the structure to collapse into contradiction. It remains predictive. It remains testable. It remains astonishingly accurate. Take the vacuum again. Once modern physics says that empty space is structured by fields, The first instinct is often to assume that all boundaries have dissolved. If the vacuum is active, if quantum processes can contribute from seemingly nowhere in classical terms, then perhaps reality is just a kind of disciplined madness. But that is not right. The vacuum is structured, not chaotic. Its contributions are lawful. You do not get arbitrary violations of causality because the vacuum is subtle. You do not get signals sent into the past because field fluctuations happen. The theory is built so that the vacuum participates in physical processes while still respecting the deeper causal order of space-time. That is a very specific kind of flexibility. It is freedom inside rules, not freedom from rules. The same pattern appears in symmetry. Symmetry in modern physics is not decorative balance. It is one of the main ways the theory keeps its flexibility under control. Asymmetry tells you that some transformation in how you describe the system leaves the underlying physics unchanged. That may sound abstract, but it has concrete consequences. It constrains the form of interactions. It determines which kinds of terms are allowed in a theory. It leads to conservation laws. It protects the coherence of the framework. Without these symmetries, the equations might allow all sorts of pathological behaviour. With them, the theory can be rich and subtle while still remaining stable. It is also worth noticing that nature sometimes breaks symmetry in controlled ways without losing order. This is another example of bending without breaking. A theory may possess a deeper symmetry in its laws, yet the actual state of the world may not display that symmetry in an obvious form. The result can be new phenomena, new effective properties, and new structures emerging from the same underlying framework. But even this is not disorder. It is a transition between levels of description. The deeper rule remains in place while the visible arrangement becomes more specific. Physics is full of cases like this. The world changes form, but the logic underneath continues to hold. This is one reason the speed limit of light survives so much theoretical development. It is not a fragile accident that newer ideas keep threatening to erase. Quite the opposite. The more successful the theory, the more deeply the invariant speed tends to be built into its core. General relativity preserves local causal structure. Quantum field theory preserves relativistic causality. Electromagnetic interactions respect the same limit. Particle processes are built around it. The vacuum structure does not abolish it. Even when the universe becomes more dynamic, more curved, more quantum, and more difficult to picture in classical terms, the limit remains one of the principles keeping the whole system from tearing itself apart. Black holes provide a striking example. They're among the most extreme objects predicted by general relativity, and at first they can sound like the universe has finally decided to misbehave completely. Gravity becomes so strong that not even light can escape from within a certain boundary. Time and space exchange roles in strange ways near the horizon in some descriptions. Singularities appear in the classical theory as places where the mathematics itself signals a breakdown of the current framework. It all sounds like a breakdown of order. Yet even here, the deeper structure does not simply vanish. The horizon is defined in terms of causal structure. Light still determines the boundary of escape. The geometry is extreme, but it remains geometric. The theory bends to its most dramatic form without ceasing to be a theory of lawful space-time. Of course, black holes also teach humility, because they are places where our current theories no longer fit together completely. General relativity and quantum theory each tell part of the story, but a full quantum theory of gravity remains unfinished. That is important to say clearly. Physics does not yet know everything about how the universe avoids contradiction in the most extreme regimes. But even here, the lesson is not that the known rules were meaningless. It is that they remain extraordinarily successful up to the edge of a deeper problem. The universe bends further than our current descriptions can fully follow, and somewhere near that edge we discover the need for a larger theory. That is not failure. It is the normal history of science. Another example of controlled flexibility comes from how light moves in curved space-time or through material media. In a medium such as glass or water, light can travel more slowly than it does in vacuum. This often causes confusion because people think it means the universal speed limit has somehow been relaxed. It has not. What changes is the effective propagation of the electromagnetic disturbance through the material as photons interact with the charged structure of the medium. The deeper invariant speed associated with causality and vacuum remains untouched. Once again, the universe allows complexity in the observed behaviour without abandoning the rule that defines the structure of spacetime itself. The same care is needed when thinking about gravity bending light. If light follows a curved path near a massive object, it can look as though the universe has decided that the straight line rule no longer matters. But in general relativity, the path is not breaking the law. It is following the geometry. What counts as the natural path depends on the space-time structure. Light is still obeying the local causal rule. The background itself is what has changed. The flexibility lies in the geometry, not in a breakdown of causal order. This is one reason physics can feel both unsettling and reassuring at the same time. It is unsettling because so many familiar certainties turn out to be provisional. Time is not universal. Space is not passive. Matter is not fundamental in the old simple sense. Empty space is not empty. A particle is not always a tiny localized object in the classical way, yet it is reassuring because the replacement is not chaos. The replacement is deeper organization. The world turns out to be stranger than common sense, but also more tightly structured than common sense ever suspected. Feynman understood this balance unusually well. He had a talent for making the strange feel concrete without pretending it was ordinary. In his treatment of light, matter, and quantum processes, the universe is allowed to be subtle, but never vague. When many possible histories contribute to a process, that is not a surrender of explanation. It is the explanation. When quantum amplitudes interfere, that is not a failure of law. It is law operating at a level where classical pictures stop being adequate. When renormalization is required to extract physical predictions from the theory, that is not the theory falling apart into nonsense. It is the theory revealing that measurable quantities and the idealized mathematical description must be related with care. In all of this, the universe bends in our understanding, but it does not break into incoherence. There is also a practical reason this matters. Science depends on the world being flexible enough to contain rich phenomena, but stable enough to support repeatable explanation. If the laws were too rigid in the wrong way, the universe might be sterile, featureless, and dull. If they were too loose, nothing could be predicted reliably. The actual universe seems to occupy a remarkable middle ground. It permits stars, chemistry, living systems, gravitational collapse, quantum interference, radiation, planetary orbits, and field interactions of extraordinary subtlety. Yet beneath that variety, stable structures remain. Conservation laws hold. Symmetries constrain behavior, causal limits survive, theories can be tested, measurements can converge. Reality is not a muddle. This is especially important when people hear about quantum weirdness and assume that the word weird means anything goes. It does not. Quantum theory is not permission for disorder. It is a more refined order than classical physics prepared us for. Relativity is not permission for paradox. It is the framework that prevents paradox while forcing us to revise our assumptions about time and motion. Field theory is not a mystical replacement for matter. It is a disciplined account of how what we call matter and interaction arise from a deeper set of structures. In each case, the lesson is the same. The universe can absorb conceptual shock without losing logical integrity. One could even say that the hallmark of a good physical theory is not that it removes strangeness, but that it contains strangeness successfully. Newtonian mechanics contained the strangeness of motion, and gravitation well enough for centuries. Relativity contained the conflict between electromagnetism and classical time. Quantum theory contained the discreetness and interference that classical models could not hold together. Quantum electrodynamics contained the interaction of light and matter with extraordinary precision. Each step was not a simplification in the everyday sense, it was an enlargement of the container. More phenomena could fit without contradiction. The universe bent our concepts, and the theories survived by bending with it rather than snapping. That brings us back to the original subject in a satisfying way. Why is the speed of light the limit? Because the universe needs a stable causal structure. Because fields and interactions must propagate locally in a coherent spacetime. Because massless excitations such as photons naturally occupy the boundary of that structure. Because massive matter belongs to a different class of motion within it. Because even when spacetime curves, or quantum fields fluctuate, or the vacuum contributes subtle corrections, the deeper architecture still depends on a consistent invariant speed. The limit is not one rule among many. It is one of the things that lets all the other flexibility remain safe, and that is probably the most remarkable part. A universe this rich might easily have been too unstable for understanding. Instead, it seems built so that complexity emerges on top of deep discipline. It can curve without losing causal order. It can fluctuate without losing predictive power. It can support particles, fields, radiation, and observers who measure things differently, yet still remain one coherent world. That is not a trivial achievement. It is the reason science can exist at all. From here, the final step becomes less mysterious and more personal. Once we see that the speed limit of light is not a bureaucratic obstacle, but a structural principle, and once we see how relativity, quantum fields, and Feynman methods all help to reveal the hidden order supporting it, the question that remains is no longer only technical, it becomes human as well. What does it mean for us to live inside a universe built this way? A universe where the deepest limit on motion is also the thing that makes causality, knowledge, and physical reality itself hold together. That is where the whole subject stops being only a question about photons, equations, and distant theory, and becomes a question about the kind of universe we actually live in. It is one thing to learn that light has a speed and that nothing with mass can catch it. It is another thing to understand what that rule is doing for us every moment of our lives. Because the speed limit of light is not just a fact about astronomy or particle physics or the behavior of beams in empty space. It is one of the conditions that makes reality stable enough to be knowable at all. That may sound grand, but it is really very practical. A universe with no fixed causal limit would not just be faster, it would be harder to understand. Causes and effects would not fit together in the same disciplined way. Distant events could influence one another without the clean structure that relativity preserves. The order of things would become less reliable. Explanation itself would become less secure. Science depends on the world being lawful, and one of the laws that protects that lawfulness is the fact that influence takes time, and that there is a limit to how quickly it can move. This means the speed of light is not only a restriction on what we can do, it is also a guarantee about what can be done to us by the universe. It tells us that events have a local order. It tells us that information must travel. It tells us that if something happens far away, its effects cannot simply appear here without a process connecting the two places. That sounds almost obvious until you remember that the deeper we went into physics, the less obvious anything became. Time turned out not to be universal. Space turned out not to be passive. Matter turned out not to be fundamental in the old solid sense. Empty space turned out not to be empty. And yet, through all of that revision, one kind of discipline remained. Causal influence does not outrun the invariant speed. That rule is one of the anchors holding the whole picture together. For us, as human beings, this has several meanings at once. The first is that the universe is not arranged around convenience. That may sound slightly rude of it, but it is true. There is no instant access to distant stars. There is no immediate conversation across cosmic scales. There is no way to treat the galaxy like one small room where every corner can answer every other corner at once. If light from a star takes years to reach us, then we wait years. If it takes millions of years for light from a distant galaxy to arrive, then what we see is millions of years old. The universe does not shorten the process out of courtesy, and yet that delay is not merely an inconvenience. It is the reason the universe has history in the form we can observe. Every act of seeing is also an act of receiving. Light travels, and because it travels at a finite speed, the world arrives to us in layers. The moon is seen slightly in the past. The sun is seen further in the past. The stars much further still. A telescope is not only a tool for seeing far away, it is a tool for seeing earlier. That is a direct consequence of the speed limit. It means that the universe does not present itself all at once. It reveals itself through travel time. There is something deeply human in that. We often want knowledge to be immediate. We want answers now. We want distance to stop mattering when it becomes inconvenient. But nature has chosen a different arrangement. To know is often to wait. To observe is to receive what has had time to reach you. Even in daily life this is true. Light from a lamp reaches your eyes after travelling. Sound from a voice reaches your ears after travelling. A message from a friend crosses wires, waves, or fibres before arriving. The delays are tiny at human scales, but the principle is the same. The world reaches us by physical process. There is no royal road around causality. That is one meaning of the speed limit for us. It makes the universe procedural. Things happen through connections. Nothing important gets to skip the path. The second meaning is that the speed limit makes shared reality possible across different points of view. This is easy to miss because relativity is often introduced as a story about disagreement. Different observers measure different times. Different observers measure different lengths. Simultaneity depends on motion, all of that is true, but those differences do not destroy objectivity. They protect a deeper one. Observers can disagree about measurements in ways that are lawful and consistent, because the invariant speed gives them a common structure underneath. Without that structure, differences in viewpoint could turn into differences in causality itself. Then the world would not merely look different from different frames, it would stop hanging together as one world. So the speed of light, strangely enough, is part of what allows reality to remain shared even when perspectives differ. That is not only a physical insight, it is almost a philosophical comfort. The universe permits disagreement at the level of appearance, measurement, and local description, but it does not permit total collapse into contradiction. It allows different observers to describe the same lawful world from different states of motion. That is a profound kind of order. It also gives us a more mature picture of knowledge. Human beings often imagine objectivity as everyone seeing exactly the same thing in exactly the same way. Physics teaches a subtler lesson. Real objectivity is not sameness of viewpoint. It is consistency across transformed viewpoints. The world remains one world because its laws connect those viewpoints coherently. The speed limit of light is part of what makes that possible. There is also a third meaning, and this one is more emotional. The speed limit of light reminds us that distance is real. In an age of instant screens and rapid communication, we can start to feel as though the universe ought to be equally quick. It is not. The cosmos remains large in a very stubborn sense. Even the nearest stars are far enough away that light takes years to cross the distance. Galaxies are separated by scales so large that ordinary language begins to feel tired before the numbers are finished. The speed limit preserves that largeness. It refuses to let imagination abolish scale. That might sound discouraging, especially if one enjoys hopeful thoughts about racing cheerfully between stars before lunch. But there is another way to see it. The fact that the universe remains vast does not make it less meaningful. It makes our knowledge of it more impressive. Every photon that reaches a telescope has crossed a real distance. Every image of a nebula, every measurement of a galaxy, every trace of ancient radiation is the result of actual travel through real space over real time. We are not peeking casually behind the curtain. We are receiving messages that have made long journeys within the limits of nature. The speed limit gives those messages weight. This is one place where Feynman helps again. What he and others discovered about light and the vacuum showed that these journeys are not taking place through a dead void. The photons arriving from a star are not just tiny bits of brightness crossing a blank nothingness. They are massless excitations of a field, propagating through a structured vacuum, interacting according to quantum rules, and still respecting the causal order laid down by relativity. That deeper picture does not make starlight less beautiful. It makes it more exact. It tells us what kind of thing the light really is, and what kind of universe had to exist for such travel to be possible at all. There is another practical meaning for us, and it lives closer to home. The speed limit of light is part of the reason modern technology works the way it does. Not because engineers build little altars to relativity in every laboratory, but because the physical world underneath our devices obeys these laws whether we think about them or not. Precision timing systems, satellite navigation, high-energy experiments, communication networks, and countless parts of modern science all depend, directly or indirectly, on the disciplined structure of space-time and electromagnetic interaction. The speed of light is not an exotic footnote sitting in the back of the book. It is one of the rules under the floorboards. Even more basic than technology is the way it shapes our understanding of time itself. Once you learn that light speed is the limit and that time is woven into that structure, it becomes harder to treat time as the simple universal river it first appears to be. Human life still feels sequential. Breakfast remains before lunch, even in the most adventurous interpretations of modern physics, but the deeper picture becomes more flexible. Time is linked to motion, gravity, and causal order. The speed limit is one of the reasons that link exists, and for us, that means reality is both more intimate and less naive than it first seemed. The seconds on a clock are not just labels drifting over an unchanged world. They are part of a physical structure in which space, time, and influence are bound together. There is something oddly calming about that once the initial shock passes. The universe is not arbitrary. Even when it surprises us lawfully. The same rule that prevents matter from reaching light speed is also part of what lets clocks, signals, fields, and observers fit into one coherent account. The world is not arranged for ease, but it is arranged for consistency. It also means we have to be careful about what we mean by freedom. People sometimes hear about the light speed limit and think only of what it forbids. No instant travel to remote stars, no faster than light messages, no easy escape from cosmic distance. But freedom in a physical universe is never freedom from structure altogether. The most meaningful kind of freedom is what exists inside a stable order. Birds are free to fly because gravity, air, muscles, and motion obey rules. Music is free because sound obeys rules. Thought is free because brains, chemistry, and time obey rules. In the same way, knowledge is possible because the universe obeys rules. The speed limit is one of those rules. It closes some fantasies and opens the possibility of a lawful world. There is also the question of humility. The speed limit of light reminds us that human intuition was built for a small corner of reality. We evolved at low speeds, in moderate gravity, across short distances, with brains tuned to practical survival rather than invariant intervals and quantum fields. So it should not embarrass us that the deep structure of the universe was not obvious. It should impress us that we managed to find it at all. The story from Einstein to Feynman and beyond is not just a story about brilliant theories, it is a story about human beings learning not to confuse familiarity with truth. That lesson matters beyond physics. Again and again, science advances by discovering that the world is not organized around our first comfortable picture. The Earth is not the center. Time is not universal. Matter is not simple. Empty space is not empty. Light is not merely illumination. In each case, what replaces the comfortable picture is not chaos, but better structure. The speed limit of light is one of the clearest examples of that pattern. It sounds restrictive, then it becomes explanatory, then it becomes foundational. For us personally, there is also something quietly moving in the fact that we live by borrowed light, Nearly everything we know directly about the wider universe reaches us because photons travel to us. The sun warms the ground because of them. The night sky speaks because of them. Our instruments, our telescopes, our detectors, our images of galaxies, our measurements of stellar chemistry, our maps of cosmic structure, all depend on light and its relatives reaching us within the rules set by the universe. The speed limit is therefore not only a barrier to what we cannot outrun, it is the condition that allows the cosmos to become visible to us at all, and what Feynman discovered, or helped reveal with exceptional clarity, adds one more layer to that meaning. He showed that the story is not just about beams crossing emptiness. It is about local interactions, quantum fields, the vacuum, and a world whose hidden machinery can be described with astonishing precision. That matters for us because it tells us that the universe is intelligible beyond first appearances. The light reaching your eye from a distant star is not a vague miracle, it is a lawful process. The repulsion between electrons in matter is not a mysterious refusal of atoms to overlap out of social discomfort. It is a field interaction. The vacuum is not a blank nothing. It is a structured state. The limit on speed is not an arbitrary decree. It is part of the architecture that keeps the whole system consistent. In other words, what the speed limit of light really means for us is that reality is built, not improvised. It has constraints because constraints are what make a world possible. It has distance because distance is part of how events are ordered and related. It has delay because signals must travel. It has shared law beneath differing viewpoints. It has a causal structure strong enough to support history, science, and memory. And inside that structure, small creatures on one planet can still learn an extraordinary amount. That may be the most remarkable part. We are not especially fast. We are not especially large. We are not sitting in a privileged center with a perfect view. We live late in cosmic history, on a small world, under a local star, and most of the universe is unreachable to us in any ordinary travel sense. Yet the speed limit that denies us easy access also grants us a stable universe to study. It prevents a certain kind of fantasy and permits a deeper kind of understanding. So perhaps the real meaning is this. The speed of light is the limit not because the universe is ungenerous, but because it is coherent. It is one of the rules that turns existence into a connected order rather than a blur of unconstrained events. Einstein showed what happens when you take that rule seriously. Feynman helped show how deeply it runs through the quantum structure of light and matter, and we, sitting here much slower than photons and much smaller than galaxies, inherit the result every time we look up, every time we measure, every time we learn something true about a world that does not have to be simple in order to be understandable. By the time you come back to the original statement, it no longer sounds like a fact from a poster on a classroom wall. Nothing can outrun light in vacuum. That sentence now carries much more weight. It means causality has a boundary. It means fields propagate lawfully. It means matter and radiation belong to different categories of motion. It means the vacuum is structured. It means time and space are linked. It means the universe is vast in a physically meaningful way. It means the sky is a record of travel time. It means explanation has a framework strong enough to survive the strangeness of modern physics. And perhaps, at the quiet end of all this, it means something else as well. The universe did not make itself easy for us, but it did make itself legible. Not instantly, not completely, and not without many wrong turns, but legible enough that a species of very local beings could ask why light is the limit. Follow that question through relativity, quantum theory, fields, photons, and empty space, and discover that the answer was not only about speed, it was about what kind of reality can exist without falling apart,